Yeah, hi, good evening, everyone. Yeah. Okay, so today this is the second revision session for quiz 2, and today we are planning to discuss the remaining weeks 7 and 8. So before starting the session, we have also released mock 2. Okay, so I hope you have solved the questions. And if you have any doubts, so we will start from the mock questions. After completion of the mock, then we will discuss some questions from week 7 and 8. Okay, for practice. So, uh, can uh, can you ask if you have any doubt in the mock? So raise your hand. Am I audible?
Yes, sir, you are.
Okay, okay, thanks.
Yes, sir, you're audible.
Yeah, okay. So I'm sharing my screen and I'm just going through these questions from start. So if you have any doubt, just stop me. 1 second. Yeah, cool. Go ahead.
Could you please solve question 5?
Question 5 in mock. Okay.
Yes.
Yes, Shreya.
Sir, I wanted to ask about question 2 from mock. The second option, why is it incorrect?
Okay, question 2.
Yes, sir.
Okay. Hmm. So, anyone have doubt in question 1? Please open your mic and just tell me. If not, then I am scrolling through. Okay. Yes, second problem. Okay. So you are asking that why the option 2 is incorrect.
Yes, sir.
Okay. So what is the problem? Suppose we want to find the shortest path from vertex S to other node. Which of the following option is are correct? Okay. So in this
Sir,
problem,
before that question one, I have a very basic clarification.
okay.
In question one,
Yeah.
when we have equal weights in multiple edges,
Hmm.
that too on the lower side, how is
Sorry.
that it is ending up with only one path, one MCST?
No, we have to check that can we replace that similar weight vertex with another vertex in the different MST or not. Okay, so suppose if any vertex, if you have multiple edge with same weights, but all are actually selected in the one MST, then you cannot create the another MST. Okay, so you can apply simple. You
Before we get into the details, I'm just asking on a high level approach. If you have
hmm,
equal weight in multiple edges, here in this problem particularly, we have 5 edges with 2 different equal weights. In
hmm.
spite of that one, there is only one path. In spite of that one, there is only one path.
No, first thing you are talking
How
about
is it
this
possible?
path. So path things is not actually exist in this MST. Okay, we are finding out the minimum spanning tree, not path.
Minimum scan. Oh, sorry, I used the wrong word.
Okay, so
MCST, yes.
yeah. So what you can do, you can simply arrange these weights in the increasing order. You can simply apply the Kruskal algorithm on this. Arrange the weights in increasing order. Okay, after that
Okay.
just select the edge in the from the smaller weight first, and then check if any edge is creating
Okay.
cycle, ignore, otherwise just consider that. Okay, at that time you can see that at any times if some equal weight is coming in the sequence, so can you
Okay.
replace one weights by the other weights? Suppose if you are selecting first, suppose this sequence is coming. Let me 1 second. Okay.
Okay, my
Okay.
question of the equal weights in multiple edges not necessarily end up in providing the multiple
Yes, yes, no.
trees.
No, 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 no. Okay, so suppose I'm giving
Okay.
one small example like A, B, C, D. Okay.
Okay.
This is the spelling. This is the one graph. Okay, so here one is, this is the one weight. This is the one weight. Okay, and this is 2.
Okay.
Okay, and this is 3, like this, and this is also 2, or not 2 but 4. Okay, so I'm taking this example here. If you see that these two edge contains one weights. Okay, one value.
Right.
Okay, so we cannot say that this graph will contain two different MST, more than one MST. Okay, so in this case, both will be selected in the MST. So if you create the MST for this, so first you will select the smaller weights. So what are the edge with smallest weight? So this one you will select, but second will also be select. Okay, in every MST, these first two weights will always select. After that, you are deciding that next weight is 2. So this is the 2. So this is the only one possible MST for this graph.
Sir,
Okay.
so I think this is a genuine question here. So if we apply Kruskal's algorithm, right, on the left hand side diagram, there are two ways to create a MST out of this, right? So does the answer give like the number of minimum spanning tree? So I think that's what the question is asking, right? Like how many MSTs you can create.
Yes, yes.
Okay.
Yeah,
Then you have to think.
that's what it is asking.
Let
And
me
I
clear.
was under the
So one thing that can be clear, if all the weights are distinct. Okay, if all the weight are distinct in the graph, definitely one MST will be come. Okay, only one MST will be generated. So this is the clear thing, but we cannot decide based on the, if any weight is repeating multiple times. So we cannot finalize this thing that graph contains the multiple MST. Okay, so we have to check these things during the process.
Sir,
Okay.
could I ask, sir?
Sorry?
Yes, sir.
What you are
If
asking?
there are, I'm asking if all the weights are distinct, then solution will be unique.
Yeah, solution only one MST is possible if all the weights are distinct.
Okay.
Okay, but in this case, when weights are repeating, so we cannot conclude that that graph contains more than one MST. So that we have to check by the process. Okay, so what you can do is we arrange these weights in the increasing order of their weights. Okay, so what is the minimum? So this is the 3. Okay, then 3. Then what is the next minimum is 4. Only 4 is only 1. Okay, so one place. Now after that, you can see 5 is repeating 3 times. So 5, 5, 5. Okay. Now 6 is also repeating 3 times. Okay. After that, what are the remaining weights? 10 and 12. Correct? Anything is remaining? No, I think. Okay. No. So if we start the Kruskal process, so first we will select 3. So you can see that when we are selecting 3, so we cannot replace this 3 by any other weight. Okay, this is the first selected weight. Similar for the 4, if we select 4, so this is also a isolated here. Okay, so this can also be not replaced by other weights in the different MST. So this will always select. So 3 and 4 will always select in every MST. So this is selected, this is selected. Now next one is the 5. So 5 here may be selected like this. So suppose if we are selecting this 5 one first. Okay, so I am selecting this one. Now next I am selecting, suppose because this 5 is also not creating cycle, second one. Okay, so this will also be come in the MST. And next one, you can see that okay, yeah. So next 5, this 5 is also not creating any cycle.
Yes.
So all 3 5 is selected without creating any cycle. So all 3 will come in the every MST. If any repeated value comes in the cycle, then we can replace the edge in the another MST. But here you can see after selecting this 3, 4 and 5, 5, 5, no cycle is generated. in our MST till now. Okay, so that means all 5 weights will be all 3 edges will be selected with 5 weights. So after that, when we select 6, so you can see that this 6 is creating, suppose if I'm selecting this 6, okay, ever 1, so this is creating a cycle, so we cannot select this. Okay, after that, if we select this one, this is also creating cycle, we cannot select this, and also this is also creating one cycle.
And
so
the first 6 is, how is it
the cycle is done.
So
Yes,
we cannot add any more edges after 5 because it's
Yeah,
complete.
all are connected.
Yeah.
Yes. So, but still, we will just check the process if anything is missed. So you can see that all 6 are creating cycle. So this 2, 1, 2, you can see that 1, 4, 3, 2, 1. This is creating cycle after adding this 1, 2.
Yes.
And second 6 is creating cycle between 2, 3, 5. And next 6 is creating cycle between 2, 3, 6, 5. Okay. So all 3 are not possible to add in this MST. After that, only 10 and 12 remaining. So 10 and 12 is also creating cycle. 10 is creating between 3, 4, 6, and 12 is also creating cycle between this 1, 4, 3. So here you can see that only these initial 5 weights are selected in one MST. After that, we are not selecting any repeated value. So if any repeated value is not selecting, so there is no problem. So that means only one possible MST is one MST is possible for this graph. If any time, if any suppose if this 6 is selected, okay, and so like this, if in any graph, suppose we have this type of situation, okay, so like all contain 3 weights, 1, 1, 1. So we can select either this one and this one, okay. So here we have now choice, because the third one, so suppose I am giving the name like this A, B, C, 3 weights with the name, okay. So if I am selecting A and B, so we have to leave this C. We can also select B and C, this one, this choice. At that time, we can leave this A. So this will create a different MST, okay. And we can also select this A and C. At that time, we can leave this B. So that will generate another third MST. But this is not happening in our this question. So all repeated value is so here you can see all repeated value are selected. Okay. Here all 3 repeated value are not selecting. So it is not creating any problem or duplicacy. So here we can conclude that only one MST is possible for this graph. So you will always select this first 5 value. So answer for this problem is only 1.
Sir, is the solution for the mock quiz 2 uploaded somewhere?
Solution means answer is there, but detailed solution is not.
Okay. Is it possible for anybody to share the answer key at least?
Answer key you can
see. If you really put submit, you get it now.
Okay. You'll get the answer for. So detailed solution, it's not discussed also in any of the sessions? The past
no, this is the first session after releasing the mock. So here you can discuss. Okay. Yeah. So answer for this problem is 1. So only one MST is possible. So if we move to the next second one. So here the problem is one graph is given, and if you see the graph, so some negative weights we can see in this graph. Okay, so this this -4, one second, this -6, -2, or there is no weight. Okay, after that, but if we see the options, so what options are given? So Dijkstra algorithm will return the correct shortest distance from vertex S to all other vertices in the given graph. Okay, so if you remember the property of Dijkstra algorithm, so I hope you have remembered that there is one property: if graph contains the negative weights, so Dijkstra algorithm may not work. So here actually this is not true. Dijkstra algorithm will always return the incorrect output, but it may return the incorrect output. So what are the difference in between these two terms? So that options actually are these options are validating these things. So what type of graph where the dashed algorithm will not work, and what type of graph the dashed algorithm will maybe return the correct answer also. So in option A, this is saying that the dashed algorithm will return the correct sorted distance for source vertex S. So here's vertex source vertex is S. Okay. So option 1 is this is given. So dashed algorithm will return the incorrect shortest distance from vertex S to at least one vertex in the given graph because the graph contains negative weights. Okay. Third, Bellman-Ford algorithm is given. So Bellman-Ford algorithm definitely works because this algorithm is designed in that way. So it returns the correct output if graph contains the negative weights, but not negative weight cycle. So option C is correct, but we have to check that option A and B. So why option B is not correct here? So in the case of this graph, in the case of this graph, yeah, so you can see negative weights. So this is the source, this S is the source here, and if you see the all edges, only 3S contains the negative weights, and all these 3 weights are actually coming from the source to the remaining vertex. Okay, so this is the outgoing edge from the source vertex. So if you remember the process of dashed algorithm, we always start from the source vertex. So what is the process of dashed algorithm? We just mentioned that 0 distance for the source and remaining for the infinite. If you remember that, remaining for infinite value initially. So in the dashed process, so if you are coming from the visited vertex, okay, and you are looking to the neighbors after the visiting vertex, so what are the neighbors of this S in this graph which are not visited? So you can see that from S you have 3 neighbors. So the first neighbor is A, and second neighbor is that B, and third is D. Okay, so you will always select the vertex which contains the minimum distance from source. So this is the 0. After that you will check that S to A. So this is -2. So -2, that is 0 plus -2, -2. Previous it was infinite, so we will replace this weight by the current distance from the source. And H to B, so 0 plus -4. Okay, so B will become -4. And H to D, this 0 plus -6. So this will become -6. So it is creating any problem. After that, you can see that there is no negative weights. So just remember that in which case dashed algorithm will return the incorrect output with the negative weights. So in this case, because if you see this, you are coming from the visited vertex and with the negative weights, and all this destination vertex is actually not visited right now. Okay, so this type of case actually there is no problem because the distance will not decrease. This is the only final updation happening from the S on A and B and D. Okay, so I'm giving one another example when so we can understand this more clear way. So let me just take one example.
Sir, my doubt in this basically was why are we choosing the second option as incorrect even though it has negative weights and the extras
Yeah, that I'm trying to explain here because we are just talking about for this particular graph. Can we get the incorrect output for this if we apply the dashed algorithm for in this graph or not?
Okay, sir.
Okay, so that I'm trying to explain here. So let me just give you one example. A, B. Okay, 1 second. S, T, 2. No, here not this one. We selected, yeah. Okay. So minus 2. Okay, so if you look this graph, so according to the dashed algorithm is a greedy approach. In dashed algorithm, we always select the vertex and we look what are the neighbor vertex and we just check the neighbor vertex, and we also mark if we are selecting any vertex with the minimum distance from source, we also mark that vertex is visited. and after that we will never check that vertex which is already visited in our graph. Okay, so this is the Dijkstra process, if you remember that. So according to the greedy algorithm, we never change the previous decision. If we have selected any vertex uh, visited in our graph, we will never update or we will never check that vertex distance in later process. So same things happening in this Dijkstra algorithm. So what we are doing, suppose just consider this graph. Okay, if we so this is the source S, the distance for initially this is 0 and remaining is infinite. Okay, if you look this, if we visited this S first, okay, after that we will check the neighbors distance. So from S the distance of A is 3. Okay, so we will cut this 3 and distance from S to B is 2, so we will update by 2. Okay, so in the next process, according to the Dijkstra algorithm, in next process we will always check the vertex which contains the minimum distance. Okay, which contain the minimum distance. So in this case S is already visited, we will not check this. Now A and B is not visited. Now we will check which node contain the minimum distance. So here A contain 3 and B contain 2. So B contain the minimum distance. So we will select this B. Okay, and we will mark this node as a visited here, because we are selecting with the minimum distance from source. But if you check after selection of this, we will check is there any edge going from B? No. So there is no update happening when we are selecting B. So this node is now visited, B. After that, we will check the next node with the minimum distance. So next node with the minimum distance is 3. Okay, this A. So from A, if you select this from A, so there is one outgoing edge is going from this A with -2. So in this case, the current distance at A is 3. If we add this distance with the edge distance, so 3 minus 2 will become 1. And this one is smaller than the previous weight of B. But we cannot update because we have already visited B. So this is creating a problem. This negative edge is creating a problem if we are coming from the unvisited vertex to visited vertex with negative weights. Okay, so if our graph contains negative weights, we are in the process of Dijkstra algorithm, we are getting this situation if we are coming from the unvisited vertex to already visited vertex, and we are getting less distance compared to the previous minimum distance of that node. So that is the problem.
But it forms a cycle also, no, sir? It forms a cycle also, no, sir?
No, why it is creating a cycle?
Already B visited.
No, can you see, is there any cycling graph in this?
No, if we visit from A to B, then it forms like.
But according to the direction, there is no cycle.
Okay.
Okay, so S to A, S to B, and A to B.
Okay.
Okay, so here actually what happening, we have already selected B, we have marked that this is visited, and we have also note down this, the distance of this source to B is 2, and this is the answer, this is the solution for this. Okay, S to B is 2, but later we are checking that we are getting A to B, 3 minus 2 is 1, but we cannot update the previous decision according to the Dijkstra algorithm. We cannot update this because B is already visited before. So according to that, our solution is now become incorrect, because we are getting less distance from A. If we are coming from S to A and A to B, then we are getting 1 only, but we have marked the solution 2. So this is the incorrect solution. So you can just note down these things in the process. If you have any edge in the graph which are coming from the unvisited node to visited node, and that contain the negative cycles, so that will create a problem in the solution. But in this problem, which this graph is given here, you can see that this edge, all 3 edges are actually going from the visited vertex to unvisited vertex. So that will not create any problem in the solution, because here we are not updating the previous visited solution by the negative weights. So initially A, B, and D all are not visited, and we are directly updating the weights by the negative weights from S. Okay, so S we are just marking this is -2, and this is -6, and this is -4. So after that, this is the solution for this. This, what is the minimum distance from S to A is -2. So this is the correct solution. Okay.
But the final distance may be negative, no, sir.
Final distance, yeah. So S to D, you are getting -6. So this is the correct solution. So distance, yeah. In this case, you are getting -6.
If you see for every vector, the result may be negative. Huh?
Yeah. So after that, you will calculate. So you will select the next smallest vertex. So you will select A. So after that, you will calculate what is the distance from A. So A to C, you will update -2 plus 5. So this is 3.
No. If you see individual vertex wise, if S to A may be negative, no?
Yes, it may be negative according to the what input graph is given. According to that, we will calculate the distance. If it is negative, so that will be negative.
Need not be always positive.
No. So this is depend on the what input graph is given. Okay. So just remember this property. If our graph contains the negative weights, then we have to check this thing. If that edges actually are coming from the visited vertex to unvisited vertex, then it will not create any problem with the solution. If any edge is coming from the unvisited vertex to visited vertex, that will create a problem, because visited vertex we have already updated the solution for that vertex, but after that we are getting a less value from the unvisited vertex due to this negative weights. So that actually updation is not happening in Dijkstra algorithm process. So because of that, Dijkstra algorithm may fail. Okay, so in this case, if we are updating the weights of S to A, S to B, S to D, so this is the correct solution. You cannot get any lesser solution from any other edge in this graph. Okay, so this is the only possible correct solution for S to D, S to A, S to B, because this is not affecting any previous decision which we have already taken.
Then this one S to A, S to B, S to C, which is the minimum distance? The -6 is the minimum.
Yeah, -6.
Minimum distance.
Yeah, -6. -6. -6 is smaller. Okay, so next process we will select -6 then, and then we will update the accordingly. Okay,
right.
So I hope this is clear when it is creating problem. So who's asked this question? Shreya?
Yes, sir. But sir, if we go from S to B and then to A,
okay.
then the same problem comes again. Like A is already visited by S. So
Okay.
if we go from S to B and then to A, then it will be the problem you said, that since it's visited and again visiting, it will.
Okay, so S to B and B to A, you are saying?
Yes, sir.
Okay, so what is the distance from -4? Okay, so this is S to B -4, and -4 plus 3. What you are getting?
-1.
-1. So which one is the smaller?
-2.
So we will not update this.
Okay, sir.
Okay, so yeah, you will not get any smaller answer for any. Okay. So yeah, if this contain
option B, how it can be?
Yeah, option B is saying that it will return maybe incorrect output for any one node. Okay, so but in this case we are getting the correct output for each node.
To answer Shreya's question earlier, when you are visiting B, you have not visited A yet, because the weight of A is greater than the weight of B from S. So you can update it.
Oh, yes.
So if let's say the weight from S to A was, let's say, -5, then this would have been problematic, because as you were saying, and let's say or some other way there was.
Yeah, if we just update this like -2, okay, then it will create a problem, because at any time when you are reaching at this B, so at that time you can see that suppose if we have already visited this B, during the process first we will visit this -6 D, then B. Okay, but -4 then -2, this will become -6, and previous was -2. It will also, so I think it is creating cycle. No.
Sir, without getting into specifics, still why option B is a right answer?
So no, option B is not correct answer.
Option B is wrong.
The option B is wrong for this.
Actually, my main concern was that only, that why are we using Dijkstra's algorithm even if it has negative weights? But that was the only question. Now I got it.
Yeah, that is the way I chose it also, but it went wrong.
Okay, so just remember these things. Why the Dijkstra's algorithm fails actually in the negative weights.
But sir,
Okay.
Okay, sir.
if we update minus, first we update -6, and up till now -2 is not updated. So after -6 we went to -4, and after that, if we went to A, then it will be like -1.
So 1 second. But you are saying that which weight you want to change here?
Like first we go to D, right?
Okay. So in this case, if you are selecting this 0, if you are selecting this 0,
Yeah, then we go
then
to
this will become -6, this is -2, and this is -4. So now the next case, we will select this one. Okay, and from this -6 we are getting, we are going to this F. So what is the final update that is happening? 7 minus 6, this will become 1. Correct. Now we will select the next smallest. So now this is visited, this is also visited, and we will select the next smallest weight. So next smallest weight is now -4. Correct. So we will just look this -4. So from B, you will check what are the adjacent of this B which are not visited. We always check the which are not visited. Okay, so B to F, F is not visited, so -4 plus 3, so we will get -1. Okay, and -4 plus 3 on the A side, so we are getting -1, but previous is -2, so that updation is not happening here. So now we have visited this one also, B. We will select the next smallest one. So next smallest one is this A. So from A, so -2 is there, and there is one adjacent is going to C. So -2 plus 5, so this will become 3. Okay, now this is also visited. Next we will select the next smallest one is -1 F. Okay, so F, if we are selecting this, this is previous. Okay, so -1 plus 3, so this will become 2. Okay, so now this is also visited. Now only 2 remaining, so C and E. So if we look this E, so there is no outgoing S, so there is no update happening when we are selecting this, and after that only C is remaining. So from C we are getting 3, so 3 plus 4, okay, 7, but previous is -4, so we will not update this. Okay, so these are the final weight from S. So S to D is -6, S to A is -2, this is -4, this is 3, and this is 2, and this is -1. We are getting. Okay, this is the -1. So these all distance are correct minimum distance from S. Okay, so you cannot get any smaller distance from any path in this graph. So if we are applying the Dijkstra algorithm on this graph, we are getting correct answer. So these actually, if so, if we look this, if any, so if this negative weights are actually leaving the vertex which is not visited, okay, and it is going to the visited vertex, then it will create a problem, otherwise not. So here in this case, these all negative weights edge are actually leaving unvisited vertex 2 and also going to the unvisited vertex. So it will not create any problem in the Dijkstra process. Okay. So I hope this is clear.
Sir, when the weights are negative, we can apply Dijkstra algorithm, but this can give the incorrect answer or correct answer.
Yeah, so because of that, we are saying that Dijkstra algorithm may return the incorrect output. So don't apply the Dijkstra algorithm.
Yeah, sir. Yeah.
Okay, we are
But in
not
this
sure
case, this
about
is
the
getting the
what are
correct
the
answer.
yeah.
But
In this
in this
case, yeah,
specific question, yeah.
yes, in this specific question, Dijkstra algorithm is returning correct output. So this property is not always true actually. Dijkstra
Yeah.
algorithm will fail in the negative weight case. Okay,
Yeah.
so it may
Okay,
fail
sir.
in some case. So because of that, we not used this Dijkstra algorithm with negative weights because we don't know what type of input graph we are giving. So we will
Sir,
not use.
in fact, in the lecture, it is finally concluded that
Hmm.
the extra algorithm will not work for
Yeah,
negative
yeah.
weights.
This is the
It's a
general
it's a it's
general.
a global statement.
Yeah, this is global statement. Because of that, I'm saying that we are not sure what type of input we are getting for the Dijkstra algorithm. So how we can just give to the
No, no,
Dijkstra
no.
algorithm?
From the students from the background of that concluded remark
Hmm.
obviously will select the option A, no?
Yeah, so because of that, we are discussing this type of questions. So maybe some competition or some gate type of exam, this type of questions will ask. So you should know
Yeah,
why
that would
Dijkstra algorithm is
yes.
actually become fail. So you should also know the reason. Okay, if any algorithm is just mentioning
Okay.
that
No, no.
that
I'm
not
just
work.
referring to.
Hmm?
Oh, okay, okay.
Okay, you
Yeah,
should you should
I
know
take
some
that
kind
one.
of
But
example.
the point
Yeah.
here is, but the point here is, you summarized that one. Whenever there is a negative weight, the extra algorithm is no, no. That's what we really understood from the lesson. But when we apply that reference to this answer, we are going wrong.
Yeah.
So please avoid such ambiguous questions.
No, why this is ambiguous? You
Because
should
I'm just
you
taking that
no
statement
if
as a reference
yeah
and using.
because of that this is totally depends on how you are learning. Okay, if you are just learning the statement,
Yeah,
okay, that this is the wrong way. You should know why this is wrong. Because of that, this type of questions we also
okay.
including in our assignments, and you should also know the region and case and counter examples. So same things for the greedy algorithm. So some examples greedy algorithms fails. So you should know some counter example for that why the greedy algorithm is failed. So just not remember the statement only. So that will create the problems in the exam. Okay.
Okay, sir. Thank you.
So third problem, if anyone have any doubt, so this is based on the Dijkstra algorithm process.
No, sir.
Okay. Fourth one is based on the float-Warshall algorithm. If you know the float-Warshall concept, so this is also similarly based on that. And someone is asked for the
So in
fifth.
this one,
Sorry,
why option four is wrong? Why
fourth.
option four is wrong?
Yeah.
Not
So
correct.
according, if you just look the float-Warshall
Option four.
formula, huh? So if you remember the float-Warshall rule, okay. So we always look if we are finding out the distance between I to j. Okay. So we
Yes.
always so if we are looking for I to j, so we always check the all possible paths which are going through from the I to j. Okay, so by some vertex. Okay, so if you are so we always looks
Direct.
all the possible all yeah. So this is the direct. Okay, this is the direct one I to j. But then we will compare that is there any path using some neighbor in any vertex in between. We are
Intermediate.
getting less distance or not.
Okay.
Okay, so in this case, we check that I to k and then k to j.
J.
Okay, so if we are getting
And
a smaller one, okay, so if we are getting a smaller one, then we select the this path value.
yes.
So same apply we apply from this formula. So we are calculating the value for this I to j, and we are checking what are the previous solution. Actually, we are looking all possible solution Okay, so because of that, we calculate the previous matrix. So we calculate the 7 matrix for this float Warshall algorithms. Okay, not 7, sorry, n minus 1. If we have n vertex, we calculate n minus 1 matrix. Okay, so we always check the solution in the previous matrix. Because of that, this is a k minus 1. So in the previous matrix, what was the I to j distance? Okay, so this formula is wrong, because the correct formula should be what was the previous solution I to j, okay, and comma what was the previous solution from I to this k, then k to j plus k to j, like this, and then we select the minimum one. But here what is given? We are adding this I to j plus I to k. So this is not correct. Here we will select from the I to j, comma I to k plus k to j. Okay, so because of that, this formula
is in the wrong place.
Yes, so this formula is not correct to selecting the distance.
So if the plus is shifted next location, it is correct, is it?
So if you mark this comma here and just put this like here plus. So I to k, k to, yeah, then it will correct.
Right.
Okay.
I have problem in the previous question.
Previous
Third, yeah.
Yeah, this one.
So the second option, the shortest path from A to H is 6. So this is true, right?
True. This is
yes.
A to H. Okay, let me just look quickly. A to H. So A to H. You are saying this one,
right?
From this to this one. Okay. So okay, 1 second. A to H. But we are getting, you can see this path, D and then D to E and then
I. Oh, okay. Yeah.
Okay, so maybe you are directly looking the shortest path in this graph. Okay, so because of that, this is related to the dashed algorithm. So just quickly apply the dashed algorithm on this, then you will get correct answer. Okay, not by just looking the graph.
Okay, got it.
Sir, as we are discussing here Dijkstra's, so I just have a small doubt, like Bellman-Ford and Dijkstra's, like solving this graph problem via both algorithms are same solving process.
No, solving process is not same.
Okay, like
Solving
for
process is
Dijkstra's,
different, yeah.
okay, so like for Dijkstra's, we choose a single source, and Bellman-Ford also single source.
Yes, correct. So both are the single source shortest path algorithm. We calculate the path from the one single source.
For Bellman-Ford, how it process? In this graph, can you explain?
So Bellman-Ford algorithm actually, okay. So it repeat the process. Suppose actually, so if we have, how many nodes we have in this graph? So A, B, C, D. So 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay, 8. 8. Okay, 8 vertex we have. So what we will do, we will repeat the process, similar type of process we will repeat. So first for the A. Okay, so we will just repeat one time. So, we will start from the A. Suppose we are just starting the 0 value here and that infinite all. Okay, all infinite. Then we will repeat the process. We will select each vertex. We will start from A and then we will select the vertex and then we will update the distance first time. Okay, and then we will repeat this process n times. How many nodes we have? So suppose in this graph, in the first loop, so this is 0 and remaining are infinite initially. Okay, so what we will do, we will just start the process of selection. So first we will select A. So what update is happening on the each vertex? So A to B, what we are getting? So 1. Okay, so A to B we are getting 1 and previous is infinite. So this will update by 1. A to D, this is infinite, it will update by 2. A to C, this is 3, it will update by 3. Okay, so how many vertex we have? I'm just noting down that A, B, C, D, E, F, G, H. Okay, H. Yeah. So first we are selecting this A, and then we are updating the graph. Then we will select the B. Okay, and in this B, if we are selecting this B, then what update is happening in the graph? Okay, so from B, the current distance is 1 and 1 plus 3. Okay, so same things, we will not visit the vertex which is already visited. So this is now visited in this first iteration. So B to D, so this 1 plus 3 will become 4, and previous is 2, so we will not update this. 1 plus 5. Okay, so this E, so B to E is 1 plus 5, 6, previous is infinite, so we will update this by 6. And B to G, so 1 plus 6, it will become 7. So we this update is happening from B. Now we will select this C. Okay, and similar things we will repeat for all nodes. Okay, so when we are selecting B, C, D, E, F, G, H. Okay, what update is happening? So this is the one cycle. Then we will repeat this type of cycle. Total, how many number of nodes we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 times.
Sir, so it's a like a long process. So we can expect this kind, like solving this type of problem in quiz.
No, we are giving the Dijkstra algorithm for this type of problem. We are not giving this long process. So Bellman-Ford type.
Okay, sir. Okay, sir. Okay.
Yeah. So the process is different. One second. So problem number 5. Yeah. Yeah, someone is asked this one, problem number 5.
Yes, I did.
Okay. So in this case, so here this question is asked that let G be a complete directed graph on 4 vertices having 6 edges with the weights being 3, 4, 5, 6, 7, and 8. Okay. So here weights are given, total number of vertex are given. So I'm just creating the vertex like 1, 2, 3, and 4. Okay. And these are the so if you just draw the complete graph for this, so only 6 edges are possible. Okay, so you can just like draw like this. So this is the complete graph. Total we have 6 edges, and weights are also given 3, 4, 5, 6, 7, 8. But that weights are not given on any particular edge. Here the question is the maximum possible total weight that a minimum weight spanning tree of G can have. So what are the maximum possible weights are possible for any minimum spanning tree for the given this type of graph? So here all possibility we have to check. So this 3, suppose if we are just taking this first weight 3, so this 3 weights can be on any edge. Okay, so like 3, this may be at this place on any edge like this. So we can just so there are multiple possibility of this, how we are putting these weights on the edges in graph. Okay, so out of this all possibility in the graph, so which graph contain the minimum spanning tree with maximum possible weight? Okay, so that things is asking here. So here you can see that all weights are distinct: 3, 4, 5, 6, 7, 8. So if we put this first 3 weights, so if you just figure out the Kruskal algorithm on this, so 3, 4, 5, 6, these are the increasing weights. Okay, 3, 4, 5, 6, 7, 8. So if always first weight will be selected 3, correct? So if this 3 comes on any position in this graph, okay, so that edge will definitely be selected. So this 3 weight will definitely be selected in the minimum spanning tree. So it doesn't matter in which edge it is coming. This 3 weights is coming on which edge. So this will definitely select, because this 3 only single edge is not creating any cycle. Okay, in any graph, single edge cannot be create any cycle. So if I'm just draw this like 1, this 2, or like this 2, and this is 3, and this is 4. Okay, so if you just mark single edge on between these any nodes, so that will not create any cycle. Okay, so if I'm just putting this like here with 3, so this is not creating cycle. That means this 3 will definitely select in the minimum spanning tree. Okay, similar, after selecting this, if we are just looking the next smallest weight, this is 4. So same thing, 2 edge cannot create a cycle in the graph. Okay, that means 3 and 4 will definitely select in the MST if these weights are coming on any edge in the input graph. Okay, suppose this 4 weights is coming between 2 and 4, and 1 or 2, and this 3 or 4, or 1 or 4, any edge, if this is coming 4, that will definitely select. Okay, so I'm taking like this, suppose this is coming on this here, so this is selected now. So 3 plus 4, this will definitely come in the output. Now we need to select next weight, so 5. Yeah, if we just talking about 3s, so 3s can create a cycle. Okay, in graph 3s can create a cycle. So if you look this next 2 weights, so 5 and 6, suppose if this, we are looking this smallest one first, 5, so there is a chance maybe this 5 weights create a cycle if it is coming between 2 previous selected edge, 3 4, like here. Suppose if we add this here, suppose I'm just putting like 3 and 4 here in the original graph, if this 5 is coming on this edge, so this edge will not be selected in MST because it is creating cycle between this 1 3 and 1 4. Okay, so this will not be selecting in MST because it will create a problem. Okay,
so but here this 5 can come to 2 4 also now.
Yeah, that can come. But what we are looking the maximum total weight. Okay, so okay, according to you, if this is coming on this 5, so now we got this MST. Now this is complete. So what weight we are getting? 3 plus 4 plus 5. So this is total 12.
Yes.
So this is one possible MST if we are looking in this way.
But not the maximum.
Yeah, what happened if this is coming on this position 5? Then it will not select. Now the next one will be select 6. Okay, so say if this 6 is coming on any as like here or here, any place. Okay, so that will be selected. So in this case, you will get 3 plus 4 plus 6, 13. Okay, so only these two possible weights are possible for this type of input graph, 12 or 13.
Yeah, but instead of 6, it could be 7 or 8 as well, right?
Why? How you can select 7 before 6? So either 5 will be selected or 6 will be selected. There is no other possibility.
Sir, so how we are selecting 6 before 5?
Yeah, because we have to think that if this 5 is creating a cycle between this 3 and 4 edge, so we will not select this. Okay, so there are two possibilities. If this 5 is not coming in between cycle, so that it will select as the third edge. So in that case, we are getting this 12 answer. If this 5 is coming in and creating a cycle in between 3 and 4, then we cannot select this, and we will move to the next smallest weight, that is 6. So that will be selected. So in that case, we will get only this 13 answer. So otherwise, you cannot get any other possibility. Okay, you cannot get directly 7 or 8 in this case. So you have only two choice. One spanning tree you are getting 12, and one case you are getting 13. So which one have the maximum? 13.
No, sir. 6 also can create a cycle, no, sir.
If 6 is creating a cycle, then 5 will be selected.
No, if 6 is creating cycle, we have to choose 7 only, no, sir.
No. Can you just tell me how 5 and 6 both are creating cycle in any graph? Then you can move to 7. If we are looking the cycle case, so 3 and 4 we have already selected in every case. After that, only one edge can create a cycle in between. Okay, so that edge maybe contain either 5 or 6. If it contain 5, then we will select 6. If this contains 6, then we can select 5 next edge.
Since like you are omitting 5 and choosing 6, we can omit 6 and choose 7 also, no, sir?
No, you can select only 3 edge in the spanning tree. Okay. in this example, you can only select, so you have only 1, 2, 3, and 4 vertex in this graph. So how many edges required to connect all the 4 vertex? Only 3. So that means you have to select only 3 edges for the minimum spanning tree in the graph. You have already select one with the minimum 3. Okay, one you have to only select with 4. So after that, only one edge can create a cycle. That weight, that as maybe contain 5 or this 6 or maybe 7.
No, after selecting 3 and 4, if you choose 8, that maximum weight will come, no, sir.
Then it will not be the minimum spanning tree, na? We are looking only minimum weight spanning tree.
Then what is the meaning of the maximum possible total weight means?
Yeah. So out of all possibility in the minimum spanning weight, okay, minimum weight spanning tree, which can contain the maximum possible weight?
Then maximum possible weight means 2 plus 3 plus 8, no, sir.
That will not be possible, no, because you have to select the minimum edges. How can you select 8?
No, minimum edges. No, minimum edges means we can select 6, 7, 8, no, sir.
But before 7, you have to select 6, na.
Here we are creating minimum spanning weight, minimum spanning tree. Okay,
no, the maximum weight should come, no, sir. So the last 3 weights we can choose, no, sir, for 3 edges.
But you are, I think, missing this term, minimum weight spanning tree. You are not creating now minimum weight spanning tree. According to the minimum weight spanning tree, your total weight should be minimum.
Then they have given in the question the maximum possible total weight means what?
Maximum possible total weight that a minimum weight spanning tree can have. We are creating a minimum spanning tree for given input graph. Okay. So what are the input graph are possible? Okay. And out of this possible input graph, what are the possible minimum spanning tree that we are looking?
Then instead of 6, 5 also we can choose, no, sir.
Can you just give example how you are selecting this 5 and 6?
No, you already chosen 3 and 4.
3. According to the minimum spanning tree process, you will always select from the minimum
weight. Okay.
So 3 and 4 you have already selected. Suppose 3 is coming here, 4 is coming here. Then how you will move to directly 7 and 8?
No, okay. 5 we can select, no, sir.
5 we can select, so that I am selecting now. Suppose if 5 is coming here, so we are selecting here. Okay, so 3 plus 5 plus 4. Okay, so we are getting 12.
So this is the MST, no, sir. Minimum spanning.
This is MST.
Then this may be the answer, no, sir.
This is the one possible MST. Suppose if our graph is like this, so one first I am creating the graph. Okay, so 3. So here graph is not given. Here only weights are given. You don't know what type of input graph is. Okay, so I'm just creating like 3 and 5 and 4 and like 6 and 7 and 8. Okay, so this is one input graph is possible. In this graph we are getting 12. Okay. But another input graph is also possible like this. So 1, 2, 3, 4. Okay, where 3 is coming here, 4 is coming here, and 5 is coming here, and then 6 and 7, then 8. Like in this input graph, how much weight you will get for the MST? 3 you will select, 4 you will select. Then after that you cannot select 5. Because 5 is creating a cycle in this graph. Then we can select 6 only. So we are getting 13.
In the first graph, you are not down now. That may come now, sir. 8 we can choose now. 3, 4, and 8. Then in the left hand side, you have first drawn on figure. No? In the left hand side, first this one 3, 4, 8 we can choose now.
Then it is MST?
Not MST. But okay, 3, 4, 6. In this what is MST?
Yeah, MST means you are creating a tree for the given graph that should contain the minimum weight.
Okay, so 3, 4, 5 in this, isn't it?
So in this input graph, you can select 3, it is not creating cycle. You can select 4, it is not creating cycle, and you will select next minimum. This is 5, it is not creating cycle. After that, all 3 are connected. All vertex are connected.
Okay.
So you are getting 12 total. So this is minimum for this graph. This 12 is the minimum possible weight for the spanning tree. Okay, but this is also a possible input graph. But in this case, you can select 3, then you can select 4, but you cannot select this 5 edge because it is creating a cycle between 3 and 4.
Okay.
Then in that case, you have to select the next smallest weight. If we will ignore this 5 because it is creating a cycle, then we will select the next greater value. So next greater value is 6. So we will get the minimum spanning tree for this graph. So if you just find out the MST for this graph, so total weight we are getting 3 plus 4 plus 6, 30.
So out of these two, the maximum we have to choose.
Yes. So out of all possible input graph, only this 2 case you will always get 12 or 30.
Any other possible graph is there?
No. How you can get other? Because when we are selecting this 3 and 4, this will always be select. Okay. So in the next edge selection, only one edge will create cycle. So that edge maybe contain 5. Okay. So in that case 5, that we will ignore that edge, and next edge will definitely not create a cycle, because 2 edge cannot be create cycle between 2 edges. Okay, so if we have select this 3 and 4, so only one edge can create a cycle between 2 edge. So we can ignore only one weight. If this 5 is coming, then we will select the 6. If any greater weight is coming, so like this, so 3 we are selecting and 4. Suppose if 4 is coming in this here. Okay, so here you can see 8 is coming. Then we will not select. Why we are looking this 8? We will select 3, then 4, and we will check the next greater. So suppose this is like 5. So this will be selected. This will not create cycle. Okay, so all possible input graph, only you will get either 12 or 13. So out of these two, what is the maximum? 13.
Likewise, we have to conclude. So the number of the weights we should take in the same order given in the question.
No, there is no order. This is just given it that graph have 6 edges and that contain these weights. So what order you are following here in this?
3, 4, 5, 6, 7, 8 like that you are following.
No, this weights order is given, but edge order is not given in the graph. So what edge order we are following in any particular graph? So, but according to the Kruskal algorithm, we always select from the smaller one.
Okay.
So can we move to next?
So this is 5th, and to next 6th one. This one. Okay.
So path given by Prism and Kruskal algorithm will be same.
Path?
Like the path of edges, the vertices.
No, first thing, don't use the term path in the MST. We are not calculating the path in MST. We are just calculating the edge, total number of. So we are just creating a tree. Tree means there is no cycle should be there in the graph, and that weights of the all edges in the tree should be minimum in all possible case. Okay. So what you are asking that now? You are asking that unique tree.
Maybe I found that question, then I asked.
Okay. So yeah, unique tree, we can say that if all weights are distinct in the input graph, then both algorithm, Prim's and Kruskal algorithm, will generate the unique spanning tree. Okay. But in the case of duplication, when the edge are duplicate, edge contain the duplicate weights, so in that case, the Prim's or Kruskal may have written the different tree, MST. with the same minimum cost. Okay, tree may be different, but minimum cost will be same. In the case of the duplicate weight value in the graph.
Why, sir? Can you show?
Huh. So, like the example, one second. So same thing. So A, B, C, D. Okay. If we have all distinct weight, so like the previous problem, so only one unique MST will be generated. So suppose I am giving like this. So 1, 2, 3, 4. Okay. So you will always select. So if you apply the Kruskal algorithm, if you apply the Prim's algorithm, so the process is different, but you will always get only one answer for this. So A to B, so on this edge will be selected and this one C. So like this 1, 2, 3. This will come in the output. So both algorithm will generate same. This is a tree actually. Okay, this is a tree, and the weights of this tree is 1, 2, 3, total 6. Okay, so if you apply the Prim's algorithm or if you apply the Kruskal algorithm, both will generate the same tree structure and with the same cost. But in the case of A, B, C, D, like this. So 1, and we're selecting like this 1 and 1. This is 2, like this. Okay. No, this is not correct. Example. So let me just include this one. Suppose this type of graph is given. So in this case, multiple MST is possible. Okay. Yeah, in this case, multiple MST is possible. So you will select either A, B, C, sorry, A, C, and B and D. Okay, and you can select this either one. Okay, and you can select this one. You can just ignore. One second. Yeah, please turn off your mic if you're not asking any question. So in this case, you are selecting this one, this first one, this one, but you have to skip this cyclic one. Okay, you cannot choose this. After that, either you can select this AB, this 2, or you can select maybe this BD. Okay, this one, this is also 2. So you have multiple choice here to select. So there is no provision in the Kruskal algorithm and Prim's algorithms. Both have the different logic and different algorithms. So any algorithm may select any edge with the same. So if you are applying this Kruskal algorithm, so maybe Kruskal algorithm will select this AB edge first. But maybe Prim's algorithm, so where the process is totally different. So Prim's algorithm may be different, this BD. Okay, but the total weights of the minimum spanning tree will be the same. So in this case, so 1 plus 1 plus 2, so you will get 4. Okay, but maybe Kruskal algorithm will return this answer A, B, A, C, B, and C, D, and D, B. Okay, so and Prim's algorithm may return like this answer. So A, D, and B. So like this, if it may return like this. Okay, so this is also 2, and this is 1, this is 1. Okay, so 1 plus 1, and this is 2. Okay, so total 4. Because both process is different, so they can select the different edge with the same weights. Okay, and Kruskal algorithm may select the different. But answer will be same, but the tree will may be different. So here you can see that here we are connecting AC and then CD and then DV. And in the different one, we are selecting this CD and AD and then AB. But we are getting the same 4 value. So we cannot say that Prim's and Kruskal will always generate the unique tree, but it will always return the minimum cost. This is correct. Okay. But in the case of distinct, only one MST is possible. So definitely both will return the same answer. Okay, so sixth problem. Anyone have a doubt in this?
No, sir.
Okay. Yes, seventh one.
Yes, sir. I have a doubt in question 7.
Okay.
Sir, there is any formula for this?
Yes, sir.
Let me
Is there
check.
any formula?
Yeah, I'm looking this. So BFS is performed in the binary tree beginning from the root vertex. Let the distance of the root represent the number of edge from the root to that node. Okay, so distance definition is given in the problem statement. Okay, a node V is at distance 4 from the root and is the last visited vertex in this BFS traversal. So then the maximum possible number of nodes in the binary tree is. Okay, so here actually this distance is given 4, and how we are just define this distance is by the number of edge in the path from root to the last visited node. So in this case, so suppose what is the structure of binary tree? So every node will contain 2 child like this. Okay. So and in this problem asking that what is the maximum possible number of nodes in the binary tree. So that for this case maximum possible number of nodes, that means our binary tree should be full in each level. Okay, then we will get the maximum number of nodes. And in this case this distance is given 4, so we are counting the number of edge in the path. So that means we have to come like this. How many levels we have to come? So 1 2 3 and 4. So you can see that for 4 distance, so 4 edge should be there in the path from root to and leaf node. This is the leaf. Okay, in our binary tree. So 4 edge should become. So if we draw the binary tree for this, so like this. Okay, now you can see that in each path from root to leaf, only 3 edges are coming. So that means the distance is 3 possible. Now we will move to the next one, that 4. And we are looking for the maximum possible answer. So we will just fill this also. Okay, in this manner. So that means this is a full binary tree. This is a full binary tree with the distance of 4. And we are saying that the last visited node. Okay, so suppose we have this node is the last visited node, and distance of this visited node is 4. So you can see that path from root to this last node is 4. Okay, so that means this is a full binary tree of distance 4, and we can calculate this by look like this. So 2, what is the distance? So that is 4, and then we will just add one more. So 4 plus 1 minus 1 in this case. So here we are using this D. So and we will get 2 5 minus 1, and this is 32 minus 1 31. And if you count this all nodes in this tree, you will get 31 nodes. So this is the maximum number of nodes in this binary tree. And if you know that BFS algorithm will always traverse the node level wise. Okay, so first if you are starting from the root node, then this nodes will be traversed, then second level will be traversed completely, then next this level will be completed, and next level this one, and this is the last level traverse. Okay, so in this manner, and we will traverse this one last. So in this manner, this is the maximum possibility of the nodes in our binary tree, where the last visited node distance is 4.
Sir, can you please explain the background for the formula buildup? The -1 is for the root, is it?
-1, no. So if you have any binary tree, suppose you can simply generate the formula for that type. Okay, so in the case of height, so height definition is also given in the questions most of the time. Suppose if we are considering that height of the node, single node is 1. If we have single node, height is 1. Okay, if we have more than if we have empty binary search tree, h equal to 0, height is 0. Single node case, h equal to 1. And in this case, we have more than one node, so that we will just check the what is the longest path from root to leaf. Okay, and we will count this number of nodes in this path, and then we can define the height. So in this case, what is the longest path from root to leaf? Only one? Okay.
4.
No, in this case.
This is only one.
So only one path is so you can see in path how many nodes are coming. So 2 nodes are coming, so we can define h equal to 2 for this. Okay, and based on this you can generate the formula. So if h equal to 2, you have 3 nodes, so you can just define 2 to the power h minus 1. So 2 to the power 2 minus 1, you will get 3. Okay, and here
what you are given, what you are given is 2 for h plus 1 minus 1, no?
So this is distance actually. Here actually we are just calculating the distance in different way. We are counting the edge. Okay, we have to update our formula according to the given definition. So here in the below case, if height is given in this manner, if we are considering the node, single node as a height 1, then we will just use this formula. If we are counting the number of edge as a height, so in that case we have to add one value in the distance. So here we are doing these things. Okay, so we are adding this, or you can simply verify this thing also. Okay, so if you are using this distance as a number of edge in between the path, so you cannot use this like 2 to the power 4 minus 1. What you are getting 15 only, but in this case you can see that we have 31. So this formula is not correct. So you have to just update your formula according to the definition of distance or height. So 2 to the power 4 and then plus 1 and minus 1, you use this formula. Then if
but here this statement, the 4 nodes from the root,
no, this distance definition is given here. If you read this statement, the distance of a node represents the number of edge from root to that node, last node. Okay, visited node. Yeah.
So you are counting the edges here, not the nodes.
Yeah. Yes. So because of that, we will add 1 in the formula. Okay. So based on the definition, so suppose if sometimes it is given that height of the single node is 0, h equal to 0. So in that case, you have to just update your formula like this. So what is the height of this tree? So height of this tree is so in this case you are counting the number of edge. So you will get this h equal to 1. So formula will also be changed. So 2 to the power h plus 1 then minus 1. This will become formula. But if single node height is given 1 or empty node height is given 0, so that means they are considering that single node counting in the path. So in that case, you will use 2 to the power h minus 1.
Thank you, sir. Because there's a confusion always now between node and the path.
Okay. So next is this 8th one. Any doubt in this?
No, sir.
Okay. So if anyone have any doubt, please just open your mic and ask me. Okay. Priority max heap. Okay, this one, the 9th one.
Yes, sir.
Okay. Yeah. So here we are talking about 3 array max heap. Okay, so 3 arrays, simply binary, we use the binary term. Okay, so bin means two childs. The node can contain 2 child. So here 3 array, this term is used. That means node can contain 3 child. Yeah. Okay, so we are using 3 child max heap, like like a binary. So definition is clearly given in the question also. Okay, so but instead of 2 child, nodes have 3 child. Okay, and we are using this structure for the heap. So every node will contain the 3 child. Yes.
Sir, can you zoom a little bit?
Okay. 1 second. This fine?
Yes, sir. Thank you.
Okay. So here we are using this structure, 3 child structure, and we are creating a similar max heap, which we have already learned. Okay, with the binary max heap. Suppose the element these are inserted in the order or into 3 array max heap. and we are getting this max heap finally. Which one of the following is the sequence representing the resultant heap? What is given? Okay, suppose the element 6 1. Okay, so this structure is given, already given, and we are adding this sequence one by one into the current max heap. So if we create a this 3 children max heap, so what type of max heap we will get? So 10 will become root. After that, this 4 will become one child, then 5, then 7. Okay, the next 2 and 3. So we have currently this max heap with 3 child structure. Okay, after that we will add this 3. So according to the insertion of in the max heap, so we will always insert at the last position. So last position is now here is this one 6. Okay, we will insert 6 here, and during the insertion process we will always compare the value with the parent. Okay, because in heap, max heap or min heap, we always maintain the relation between parent and child. In min heap, parent should be smaller than the child. In max heap, parent should be greater than the child. So in this case, we will just follow the process. So 6 we will compare with the parent. So 4. Okay, this is a max heap, but this is not following the rule. 6 is coming in as a child. So we will just swap this. Okay, we will just swap with 4. After that, the 6 will come at this place. Now we will compare this 6 with the parent of this 6, 10. Now this is okay because parent is greater. So after this one swapping, this 6 will come at this place. So 10 and 6, 5, 7. Okay, and this 2, 3, and this will become 4. So swapping will be happen between 6 and 4. So always compare with the parent node during the insertion time. Next value is coming 1. Okay, so 1 will be inserted as a first child of this 5. So 1. So what you can see 1 and 5 is not in the okay, this is already in the correct order. So 5 is greater than the 1, no problem. Then next insert is 12. So 12 will insert as a second child of this 5. So here you can see the parent child relation. 12 should be come at this so yeah, here 5 is smaller than this 12, so this is not in the correct order. So first we will swap with this 5. After that we will look the next parent. Okay, so 12 and 10, again this is not following the rule. 12 will swap with the, so 12 will come at this place, and then this will be replaced with this one. Okay, so first swapping will be happen 12 and 5, so 5 will come at the bottom. Then next swapping will happen with between 12 and 10. So 10 will come at this next place. So I'm just drawing this. So finally 12 will come at the top. 6. This will become 10, and then 7, and this 2, 3, and 4. Okay, so this will become 1, and this will become 5. 5. Okay, second child. So now this is a max heap. Now we will add 8. So if we will add 8, so you can see that this is following the rule. Parent is greater, no problem. Now next we will add this 9. So 9 will become the first child of the 7. So 9. Now this is not following the rule. Okay, so 9 and 7 will swap. So in the final case you will get 6, 10, 7, 2.
Not 7, sir, 9.
Yeah, 9. Sorry. 3 and 4. Then 1, 5, 8, and this will become 7. Okay, now all nodes are in
Option C.
Yeah, all nodes are inserted. Just read in the sequence manner. So 12, then 6, 10, 9, 6, 10, 9, then 2, 3, 4, 1, 5, 8, and 7. So this should be the sequence. Okay, so just match with the option.
Yes, sir, clear.
So next one is the
If it is a min heap, can it be directly reverse?
the same rule formula we will process we will follow the same. Okay, but we will look the relation in the different reverse manner. Okay, parent should be smaller every time.
The root will become minimum, is it?
Yeah, so that is depend on the problem, what problem is given. Okay, so if minimum is spending minimum min heap is given, that the input will be different.
No, only difference is the root is minimum. No?
Yeah, not only root,
all the other,
all parents. will be smaller than the child.
Sorry, parents and root. Okay.
Okay, not only root. Okay. So yeah, this next.
Sir, in the case of minimum heap, the insertion will be in the last or the topmost?
Same. We will follow the same process of insertion. We will just compare with the parent. If relation is not in the correct order, so parent should be smaller in the min heap case. So if parent is not smaller, then we will swap.
No, you have to insert the first element in the below position only.
So we will always insert at the last position, last possible position in the binary heap.
For both the heaps.
Yeah, both the heaps. We will always insert at the last position. Then we will start comparison with the parent, and we will shift accordingly. Okay. Yeah. Next problem is this AVL tree related. Any doubt in this?
Sir, I didn't try. Can I try it now?
So okay, first thing, this is not. I have already discussed this in detail. How we can create a AVL tree? What are the rotations? So you have to just look that session. Okay, because that is very actually big details, and I cannot explain all the things again here. But I am just creating how we will create the AVL tree for this. Okay, so you should know how we will just create the AVL tree. I'm just following that process. Okay, so here one sequence is given. We are creating the AVL tree for this given sequence, and after that we will just look what elements are coming on the leaf after in the final AVL tree. So insertion in the AVL tree is similar to the binary search tree. Okay, so we always use the binary search tree property in the AVL tree. Okay, so that property should be we will use in here during the insertion process. And after that, we will check that if our tree is balanced or not. If not balanced, then we will apply the rotations and we will make balanced tree.
Sir, in the mock test, the notation which is a multi-choice question or multi-choice question is not given, sir.
For this problem?
Whether it is multi-choice question or
multi-choice. This is multi-choice.
Where it is given?
You can just understand by this
select. Generally, along with the question, it will be given, no, sir.
Okay, let me check.
In the mock test, it was not given actually.
No, in the previous question, it is where it is mentioned that this is MCQ.
No, that's what I am saying. Usually, in the examination, it is mentioned along with the question.
In the final paper, that it will be mentioned because that is actually they are using TCS software, so where they have to put.
Then this should be mentioned here also, no, sir, mock test also.
But I think this is clearly understandable by this selection boxes.
Yes, in the center we don't have this selection box. All the options are in circle.
But at that time you will get this statement. Yes. This is multi-select or this things, no?
Yes, sir.
So they are following some specifics for software for this, but here actually we are using this. I think in normal assignment we are also not mentioning this MCQ. This is MSQ.
Yes, sir.
Not take this. Okay. So you can just simply understand in our portal by this selection boxes, because in the MCQ you cannot select more than one. Okay, so you cannot select more than one option here.
But some questions may have more than one answer.
No, which question have more than one answer for this round circle?
No, not in this particular question. Some questions may have more than one answer.
Yeah, so in this type of question, you have the choice. You can select multiple answer, but you cannot select multiple answer for this type of box in our portal. Okay, so this is I think
by selecting we have to know.
It's also obvious from the question because it says which of the following nodes would be the leaf.
Yeah, we also mentioned these things. Okay.
Can you show the answer?
Answer is this 5, 32, 35, 72. Okay, so I am creating the AVL tree for this. What is the process to solve this? So we will just take one element every time. Okay, so one element we will insert at one time. Okay, after that we will check this is our tree is balanced or not, and we will follow this process. Okay. And in this case, we have only first node is 36. So we are inserting this 36 node in our empty binary search tree. So 36 will insert first. Okay, this is single node. In the AVL tree, we will just calculate the balance factor. So balance factor calculation formula is what is the left height minus what is the right height, absolute value. Okay, so HL minus HR, and what is the absolute value. And height of the left height, you can simply count the number of nodes in the longest path in the left side. What is the longest path? What are the number of nodes in the longest path in the right side from root to leaf, any leaf. So you can just you can either count the number of edge or either count the number of nodes in the path. Okay, both are fine. So here actually left height is 0, so there is no nodes in the left side and there is no node on the right side. So we can simply just we will just looking in the lower part. So 0 on the left, 0 on the right. So 0 minus 0, 0 balance factor. Okay. So according to the AVL tree, this balance factor should always be greater than equal to 1. Sorry, less than equal to 1 for the balance. If it is greater than 1, then that means this is not balanced. We will apply the rotation. So in this case, we are getting 0, no problem. Okay. Now we will insert 40 in the current binary search tree we have. Okay. So 36 we have and 40. So we will compare always from the root node, and then we will just look where is the empty place, and then we will add. So 40 is greater than 36. So that means according to the binary search, this should be come on the right side. So 40 is greater than 36. We will look the right child. So right child is empty now. So we will add the right child, this 40. Okay, so now it becoming binary search tree. Now we will calculate the balance factor again on each node. So what are the left height of this 40? 0. What is the right height of this 40? 0. So 0 minus 0, balance factor for this 40 is 0. Same thing we will calculate for the 36. Left height is 0, right height is 1. So we are not counting the nodes on the right side. Okay, we are counting the path. What are the number of nodes which are coming from root to leaf node? Okay, below without including this root. So only 1. Okay, so 0 minus 1 minus 1, or we are taking this absolute value, so 1. So you can see that all nodes contains the balance factor which is smaller than equal to 1. So both are okay. So this is also a balance case.
Here we are counting the edge.
You can count the edge. You can use any specific formula, but just maintain the formula in whole process. Okay, so both will give the correct answer. So if you're counting the number of edges, so yeah, that is also fine. So 32, yeah, next we will add 32. Okay, so next I'm just adding 36, 40, this is the current one, and 32 is smaller than 36. That should become on the left side, and left is empty. Okay, so we will add 32 here. So after adding this, we are getting what is the balance factor for 32. So 0 left height, right height is also 0. So 0 minus 0, 0. Same for 40. So always you can directly mention if node is leaf node, balance factor is 0. Okay, so left is 0, right is 0, 0. 36, left height is 1, right height is 1. Okay, if you are counting the number of edge. So 1 and 1. 1 minus 1, 0. So this is also okay. No rotations required. Now next is 18. So next is like 36 and 32, 40. Okay, so 18 is smaller than 36. Now we need to check left side, but left side is also contain one node. We will compare this by this. So 18 is now smaller than 32. Yeah, that should come on the left. So left is now free. So we will add here 18. Okay, so now again, so 0 and 0. Now what is the balance factor for 32? So 1, left height is 1, right height is 0. So 1 minus 0, 1. Same for 36. So left height is 2 here. Okay, so longest path is 36 to 18. 2 edges coming. So 2 and right height is 1. So 2 minus 1 is 1. Still it is okay. Now 72. So if we add 36, 32 and 18 and 40, so 72 is greater than 36. Okay, move to the right.
Sorry, excuse me. 36 minus 0, 36 for 36 it is 2, no sir?
Where?
The left,
This,
left
this
graph.
one. This one. So what is the left height?
2.
What is the right height?
0, 1.
Right height is 1.
1, okay.
Okay. So now the 72 is greater than 36. Move to the right. Compare with next node. Okay, so 40. Yeah, 72 is greater than 40. Move to the right. Right is empty. Now 72 is will add. Okay, here. Now we will just compare again 0, 0. And 32. So 1 minus 0, 1. Similar 40. 0 minus 1, minus 1. So we will update like 1. Okay. Now for 36. So left is 2, right is 2. Both are 2. 2 minus 2, 0. No problem. Okay. Next will be add 5. So 36, 32 and 18 and 40 and 72. Okay. So 5 is smaller than 36. Move to left. Smaller than 32. Move to left. Smaller than 18. Move to left. Left is empty. So 5 will insert here. Now in this case, this is 0, this is 0. 18, what is the balance factor for 18? This is 1 minus 0, 1. What is the balance factor for 32? So 2 minus 0. This is 2. Okay. And for 36, 3 minus 2. Okay, so 3 minus 2 is 1. And what is the 40? So this is 0 minus 1, 1. So here you can see that we are getting this balance factor greater than 1 on this 32. So that means we need to balance this part. And in this case, so we have already just tell you what type of this case is and what type of rotation we will apply in this case. So if we are getting this type of situation, so this is the case of left. So which side we are getting this 2 weights on 32? Which side height is greater than from this 32, left or right? So left side. Okay. Now just move to the child node on this 32 and look again. Which side height is greater than from 18? Okay, left or right? Left. Okay, so left. So this is the one case of LL case. Okay, in this case, if we are getting this type of case, we always apply the clockwise rotation. So we apply the clockwise rotation on the node this 32, which have the balance factor greater than 1. Okay, so we just consider this as a pivot position and just rotate this as a clockwise, one position clockwise. Okay, so we will shift all the element one position in the clockwise direction. So this 18 will come at 32 place, 32 will move to the right side one position, and this 5 will also shift it one position up. So we will get this like 36, 40, 72. Okay, and this will become 18 here and 32 here, and now 5. So after that you will calculate the balance factor. So 0, 0, 0 leaf for leaf node. So for 18, so 1 minus 1, 0. For 40, 0 minus 1, 1. And for 36, you can see that longest path is 2 and 2. 2 minus 2 is 0. So now all the balance factor is resolved. So this is the updated rotated tree. Okay. Now we will add 35 in this. So in this case, 36 and 18, 40, 5 and 32, 72. So 35 is smaller than 36, greater than 18, greater than 32. 35 will add here. Okay. So if we are adding this 35 here, so balance factor for this is 0, this is 0, this is 0. And balance factor for 32 is 0 minus 1, 1. Same for this 41. Okay. And balance factor for 18, so 1 minus 2, so 1. And balance factor for 36, so 1, 2, 3. 3 on the left side, okay, 3 height, and right is 2. So 3 minus 2 is 1. All are equal or less than 1. So this is fine.
Sir, why did it rotate from 32, sir, when we are adding?
Where? Sorry?
Sir, when we are adding the right note, it
No,
rotates.
your voice is breaking. Can you repeat? I'm not getting your voice clear.
Can you hear me now?
No, still your voice is not coming.
Like when we are adding from the left and the right side, need to rotate from the 32.
You're talking about this previous step?
Yeah, the
This one?
rotation.
Yeah,
Yeah,
this
what?
one. Yeah, rotation. This one.
Yes, sir.
Ha. So what you are saying?
Why we are rotating? What is the need to rotate here?
To make balance.
Okay.
To make balance this part, because we are getting this side the more height. Okay, so to make balance we will rotate this in the clockwise direction. So this 18 will move one position up and this 32 will come one position on the right, so that total overall height will become one less with the previous one. So you can see the label. Previous the label was from the root is one, if we count the 1 2 3 and 4. Okay, so this is the label from the root, but now after rotating, now label is become one less. So 1 2 3, one reduced.
Sir, you are comparing the left to right, which tree, sir? 40 and 72 and the 32, 18 and 5, is it?
Where, which step you are talking about now?
No, the same thing, the left rotation you are deciding. You're doing the left rotation all because the height difference is 2. It's more than 1, no?
More than one.
Yeah.
Yeah,
But
if we
now
are
the comparison is between the left and the right minor tree or the major tree right.
comparison tree means I'm not getting where you're talking. So
36.
36 where?
There is a tree coming from 30, 32, 18 and 5, no? That's one.
You're
From the
talking
root.
you're talking this tree?
Yes.
Okay. So after
But the
rotation,
tree is not existing in the previous graph, no?
no, this was the previous. So this one is the previous one. Okay. This one is the previous one. Here we are.
How is it 2 now? Okay. How is it 2?
What 2?
The height difference is 2.
Height difference is 2
How is it?
on 32 you are talking about?
Yeah.
Okay, so just check how many edges are coming on the left side in the longest path. 32 to 5.
1, 2, 3 edges are there, no?
No, from
1,
32.
2, 3.
From 32.
From 32 you have to take it, huh?
Yeah, we are
1,
calculating
2.
this balance factor for each node. If we are calculating the balance factor for 32, just look below from 32. Okay, so on 32, just look on the left side, 2. Right side, 0. So 2 minus 0, 2.
Right side.
Okay, but from 36, longest path is...
Which is the right side is the one which is not existing. The right tree, the mini tree is not yet existing, so you are comparing with that.
Yeah, here there's no right partner, so we are taking 0 height on the right height.
Yeah.
So 2 minus 0 is 2. Okay. So after that, based on the condition, we are just applying clockwise rotation on this LL rotation. So if you want to know what is this LL, or we have already discussed these things, LL and RR and LR and RL, these 4 cases in the detail. Okay, so just watch the week 7. Okay, so because it will take two hours. So I don't want to discuss all of it. Okay, so after that we have rotate this one clockwise. So we are getting this one, and yeah, someone is asked in between. I did not get what you are asking. Can you repeat again?
You're asking me or somebody else?
No. In between, someone is asking.
Ravikant is asking, sir.
Ravikant?
I got it, sir. I got it, sir.
Okay. So this is the next step, and we are talking about now 35. Okay, so 35 is added at this place, but after that, still we are getting all balance factor is smaller than or equal to 1, so no problem. Okay, so we will add this 34 now. So okay, now we have less space, so I'm just creating 36, 18, 5, 32, 35, and 40, and 72. Okay, so 34 will be smaller than this 36, move to left, greater than 18, move to right, greater than 32, move to right, smaller than 35, move to left. Okay, so 34 will add here in this case. So now just calculate the balance factor, 0 for this, 0 for this, and 0 for this. Okay, but for 35, 1 on the right, left. Okay, so 1 minus 0, 1. Okay, on 32, so longest path on 32 is right side is 2 and left is 0. So 0 minus 2, 2. Okay. Now on 18, so left height is 1, right height is 1, 2, 3. So 1 minus 3 is 2. Okay, absolute value. Similar for 40, so 0 minus 1, 1. On 36, so what is the longest path on the left side? So this 36, 18, 32, 35, 34, this is the longest path. 1, 2, 3, 4. So 4 is the longest height and 2 on the right side. So 4 minus 2 is 2. So in this case, you can see that you are getting this more than one balance factor on 3 nodes. 2 on 32, on 18, on 36. So in this case, always balance the part which on the node which are coming first from the bottom side. Okay, just look which node is coming which have the higher balance factor from the bottom side. So this, you can see that this 32 is coming first. Okay, this one. So just rotate this part. Okay, just make this part balance. So after rotating, after making this part balance, so one level will decrease. Okay, so all the above place is also reduced by 1 if you make this this part as a balance. But what is the type of rotation we will apply on this case? So we will look on the 32. So which side height is greater from 32? Right side. Okay, so we will note down this is a first R. Okay, so R, right side, and then just move to the child node of this 32 on the right and just check which side height is greater from 35, left. Okay, so RL, this is the RL case where the height is increasing on right and then left, this manner. Okay, so in this case we apply 2 rotations. First rotation we will apply on the child node. Okay, child node of the node which have the greater balance factor. So first rotation we will apply on the child node, and that rotation will apply as the clockwise, one position clockwise on 35. After that we will apply the second rotation on the node which have the balance factor more than 1, and that rotation will apply as anti-clockwise. So in this case, after first rotation, so first rotation we will get this type of tree. So 36, 40, and 72. Okay, and this side 18, 5, and 32, and after rotation of on lower part. Okay, so we will just rotate this as a clockwise. So this part, so this 34 will shift on the 35 position, 34, and this 35 move to the right side. So this 35, this will become after first rotation. Then we will apply the rotation on 32, and this is a anti-clockwise rotation. So now this 36, 18, and 40, and 72, and this 5. Now this part. Okay, so we will just rotate this part. Okay, so this part on this as a pivot position and in the anti-clockwise position. So the 34 will move at 32 position. So 34.
How we can decide clockwise or anti-clockwise?
Yeah, this is the rule of the AVL tree. So because of that, I am saying just watch the week 7 lectures. Okay, so because of that, we have all discussed all type of rotations.
Okay.
All 4 type of rotations. Okay. So you have to just remember this type of in which case which rotation is required. So this 34 will move to this 32 position, and this will shift here this side. Okay. So this 32 will come here, and 35 will add here. Okay, so after applying these two rotations, now you can calculate the balance factor. So 0, 0, and 0 and 0. Okay, or 4. Now 34, 1 minus 1. So this will become 0. 18, 1 on the left and 2 on the right. Okay, so 2 height is on the right. So 1 minus 2 is 1. And on 40, so 0 minus 1, 1. On 36, you can see height is 3 and right side is 2. So 3 minus 2 is 1. So now all place you can see that all is now resolved. So this is the final AVL tree for the given sequence. So what leaf node is coming? So 5, 32, 35 and 72. So this 32 and 35 and 72. These four are the correct answer for this. Okay.
5 is also a leaf node.
Yeah, 5 is also leaf node.
Then 72. So this type of problems takes much time for solving.
Yeah, if you know the process, you can quickly do. If you have already practiced 4 or 5 questions for this, so generally we not give the very long sequence. If you see this process, so only 2 place we need to require these rotations. Okay, only the first place we are getting this type of situation RR, so left LL rotation, and second time we got this type because we apply the rotation only 2 times. So if you know the process, you can quickly solve this. Generally we give the small sequence, so we have only 2 or 1 or 2 rotations is required. Okay, so now move to the next. Yeah, this 11th question. Anyone?
Sir, what about option 2?
In 11th one or previous one? This one?
In 11 one.
Okay, this one. Okay. Option 2 you are talking about. Okay. So you are saying that option 2 is correct.
No, sir. I'm telling about statement 2.
Okay, statement.
Like always generate prefix code.
Huffman code algorithm always generate prefix code. So yeah, this is correct. You want to know the meaning of this?
Yes, sir. Like prefix code, what does it mean?
Okay. So prefix code. So I think next problem. Let me look the next problem. Okay, so that is not here. Okay. So prefix code means if we are calculating the Huffman codes for give any frequencies. So suppose if we have some character. Suppose we have any character like A, B, C, D, E, and we have given this frequency for each character A, B, C, D, E, and we are calculating the Huffman codes by the given frequency. So for what is the first process is we will create a Huffman tree. Okay, and after creating the Huffman tree, we will generate the Huffman codes. Huffman codes is basically we will just look the path from root to the leaf node, and we will check what value is coming on the edges. So we generally take 0 value on the left edge and 1 value on the right edge, and just note down the sequence. So after generating the Huffman codes by this process, so prefix code means you will always get, like suppose if you are getting the code for A is 01, okay, and you are suppose you are getting the code for this 110 for this. 1 second. Okay, and suppose you are getting the code for C is like 010. So what is the meaning of this prefix code? So prefix code means Huffman code. So you can see here any code, any complete code of any character. So here the code of A is 01. This should not be come as a prefix in the any other code, complete code. Okay, so this 01 you can see this is also coming as a prefix in the C code.
Yes, sir.
Okay, this is not possible in the Huffman codes. Any complete code cannot be come as a prefix code in the another code. So this is not possible in the Huffman codes. If our codes is following this property strictly, so we generally set this statement, Huffman code is always generate the prefix codes.
So you are saying this coding part like 01110, these are prefix code, and Huffman always generate unique prefix code. We will not repeat in others.
Yes. So this type of situation cannot be generated in the Huffman codes. Okay. So yeah, I'm just giving one example like this 01110 and 11, and like if we repeat this 101, okay, and like 000. So if you see this type of codes, so you can see that any complete code is not coming as a prefix code in the another code. So 01 is not coming as a prefix. Like this 11 is also, oh, this is also wrong. Let me change this. So like 111, you can change. Okay. Yeah. So here you can see that this 110 is not coming as a prefix code. 111 is not coming as a prefix. So any code cannot become as a prefix code. Okay. So Huffman always generate.
If that is the case, then option 2 is not right, no?
No, actually the definition is actually different here. If we are talking about that Huffman algorithm always generate the prefix code, means that any code cannot be prefix of the another code. This actually some confusion is there in this statement, but the meaning of this statement is this which I just explained that. Okay.
So now you explained that one, the codes what you had given, it will not be repeated in any row. That's the statement you made now, no?
Not repeat means I'm just saying that any complete code cannot be come in the prefix of any code.
Any complete code cannot be in the prefix of code.
Yeah, come
but
as a
now
prefix
what is the
code in the
statement
other
given?
Yeah,
What is the statement given?
Yeah, so this is according to the property. This is the statement. Huffman code always generate the prefix code.
It should be generates the unique prefix code.
Huh. So according to the definition, this term is given in the property, but meaning is that which I just mentioned. Prefix
How
code
do you
means,
read that statement in the light of the examples what you have given? How does the statement fits in there? It doesn't fit in, no?
you can say that it is creating some confusion, but this if we are talking about this codes are prefix codes, so that means is that this cannot be come at the prefix code in any other code. This is the definition of prefix codes.
The meaning it is generating a unique prefix code.
So the other issue is option 1 is wrong. So therefore, all the other options are incorrect anyway.
Why option 1 is wrong?
Because the frequency of the leaf labeled at X has to be the frequency has to be more than the frequency.
But why the other option is dependent on one option?
No, because if you look at the options, if statement 1 is wrong, then all the other 3 options in your question have to be incorrect. No? So only 2 and 3. The only remaining correct option is 2 and 3.
No, we cannot conclude in that manner.
But that's logical, isn't it? I mean, if statement 1 is wrong, then your remaining options down there, only this 2 and 3.
You are telling that from the given options, if the first one goes out, so only the 2 and 3 is there, because no other answers are remaining there.
Correct.
Okay, okay, got it. You're talking about from this option.
Yes.
So here 1 is coming in every option.
Because that's what I do in exams. I eliminate quickly so that I can answer the questions quickly.
Okay, yeah. So if 1 is wrong and it is coming in the 3 options, so all 3 are incorrect. Yeah, that is fine. I'm just thinking about this. Yeah, you are concluding based on this.
That way, you are not choosing the statements on the merit of the content. It is just a process of elimination. You just
yeah.
But that's what I do in exams, because that's the only way you can finish them quickly.
Right.
Otherwise,
yeah, this is reverse engineering you are following. Yeah. Okay. So, but
Yeah.
don't confuse this terms. Okay, so generally we always get this type of Hoffman tree like this. Okay, so like this type. Okay, so each node and like okay. So if you traverse all the paths from root to leaf. Okay, so final actually the character is comes at the leaf node position. So we always check the path from root to leaf. So you will always get the uh, code unique code for the each character, and because we are just looking for the code which are coming at the leaf node, okay, till leaf nodes, we are not looking at the in between part. So that means any code cannot be come as a prefix, because if we look only this part of the code, so that maybe comes at the prefix position of the lower one. Okay, let me give another example like this. So suppose I'm just taking some frequency. Uh, okay, so suppose this is the character A, B, C, and D, and E. Okay, so these actually characters always comes at the leaf position. So when we when we calculate the codes for this, so we always mark that this left edge contains 0, always all left are 0, and all right edge are actually 1. Okay, left is 0. So we always read the code as a root to leaf node. So if we want to calculate the code of A, so that should be from root. So 0, 0, 0, 0, 0, 0. And similar for B, we will get this like 0, 0, 1. And for C, we will get 0, 1. Okay, so root to 0, 1. And for D, we will get 1, 0. And for E, we will get 1, 1. Okay, so because we are calculating the code till leaf, because of that, and if we are getting any code as a prefix code of the other code, so that means we are just taking the middle part of the code. If we are just taking like a 0, 0 is the code for any character, so it is not possible, because 0 and 0 is finishing at this place, and this is not a leaf, and this is not possible of the code for any character. We cannot take any code which is not coming till leaf, then it will become a prefix for the any other codes. We are always looking the code which are coming from root to leaf. So in that case, you will get this type of codes where you can see any code cannot become as a prefix from any other code. So if our codes contain this property, so these type of codes is actually called as a prefix code. Okay, so this is the definition of prefix codes.
Sir.
Okay, sir, clear.
Sir, your prefix, like when the leaf here from the level 2, the AB is below this. So when this happens, then it will be prefix.
No, but A and B cannot become in the same path.
It will be different.
Definitely because each leaf have this different position, na? So that leaf cannot become in the same, otherwise that will not be the leaf. Okay, if you just look at the path from root to leaf, so that path will always be the unique path. Okay, if you just mark this as a B, then this B is not a leaf node, no? This is the internal node. So here we are talking about the path from root to leaf. So that will always be the different unique path. Okay. So this type of codes is actually called as a prefix codes. So because of that, this statement is saying that Hoffman code algorithm always generate prefix code. So just remember these terms. Okay, this is little confused a little bit, because here we are talking about prefix code, but we are not following this property in this codes. Okay, so that any code cannot be come as a prefix. So but still remember. Okay, next problem, this 12th. So I think it is discussed as a minimum lateness problem in the beak 8. So any doubt in this?
No, sir.
No, sir. It's quite easy.
So simply,
Sir, can you tell what to do in this question? Just
okay.
roughly.
So in this case, some time required is given and deadline is given. Okay, so each job ID, this is the time required. So in the to get out the solution for this, first sort the jobs based on the deadline in increasing order.
Okay, sir.
And after that, just note down this process. You can simply solve like. So after sorting based on the deadline, so this 5 will come at the first position because this is the smallest one. And in this case, you will start from the like 0 time. You will start from the 0 time, and this 6 ID is taking 2 times. So that means you will get 2. So you are starting from 0. So 0 plus 2 is 2. So first this job will be completed. 6 job will be completed at time 2. And what is the deadline for this is 5. So if you are completing this job before the deadline, so that means there is no lateness. Lateness value is 0. Okay. If we are completing any job before or at the time of deadline, so that means we are not late. So load that we will consider as a 0 lateness. If we are finishing after the deadline, then we will just check the difference. So here in this case, we are completing this 6 job first based on the deadline that it is completing on time 2. So no lateness value is 0 for this. After that, we will look for the next smallest one. This is 6. Okay, and this job ID 1. So what time is required to complete this is 4. So we will just add with the previous end time. So 2 plus 4 is 6. So 2 plus 4 is 6. That means this job ID 1 will be completed at time 6. And what is the deadline for this is 6. So same, we are not late, 0 lateness. Now we will again start for this next job. So this is 7. Okay, so 7 is 2. And time required for this is 2. So 6 plus 2 is 8. Okay, and this is ID 2. And what is the deadline is 7. And we are finishing at 8. So here some difference is coming. We are finishing after the deadline. So what is the difference is 8 minus 7 is 1. Okay, and after that next smaller value is 8. So and what is the time required is 1. So we will add this is here 9. Okay, and finishing time is 9, but deadline is 8. So same thing, 9 minus 8 is 1 for this. So this is third. And next one is 12. So 4 we will add 4 here. So 9 plus 4 is 13. And this is ID 4. So in this case 13 we are finishing and deadline is 12. So same 1 difference we are getting. And after that 3. So the 13 plus 3 is 16. We are finishing at 16 and deadline is 14. So in this case we are 2 late. 16 minus 14 is 2. Okay. So what is the maximum value among all lateness? So this is 2. So this will be the answer. So during this process, we are just reducing this maximize lateness value. First, we are calculating the all lateness value for each job, and we are scheduling in that manner. So value of the maximum among all the lateness, that should be minimum in all possible schedule. If you change the order, of selection these jobs, maybe you will get this maximum among all lateness is greater than 2, but not less than 2. You will not get any order where you are getting this less than 2. Okay, so answer for this is 2. So this is also based on the interval scheduling. If you remember that, yeah. So this is depend on the previous one. No? Which of the following is correctly in the given problem? Okay, so this is the same. Okay, 12 and 13 are the best. So what we are doing, we are just following the always choose the job first whose required time is minimum. No. So what we are following the strategy is this one. Always choose the job first whose deadline is earliest. So if you follow the second property, you will get the correct answer. If you follow the other things, you may not the correct the may just get the incorrect output. So option 2 is correct for this minimum latest problem. And next problem is 14. So I think this is easy. You can directly use this formula for this.
Yes, sir.
Yes, sir.
Okay.
N into n minus 1 by 2.
And for the minimum, if we ask that what are the minimum number of inversion pair, then
0.
Yeah, it's 0.
It should be increasing order, like
Yeah,
1, 2,
yes,
3.
correct. Okay, so in the case of increasing order, you will get 0, or in totally reverse order, you will get this n into n minus n divided by 2. Otherwise, you have to count. So in this case, directly apply the formula. Problem number 15.
Yes, sir. Could you explain? Because I know little bit we have to divide in 7 parts because they have given median block should be 7.
Yes.
But could you
So what you can do, you can simply just divide this block into 7 each. Okay. So in this case, just write this sequence like this. So 9. Okay. And just take 1, 2, 3, 4, 5, 6, 7. This is the first block.
It should not be in increasing order, sir?
Yeah, block should be increasing in increasing order. Okay, so we will select the block first, then we will sort this.
Oh, then we have sort, not from the starting.
No.
Okay.
So 1, 2, 3, 4, 5, 6, and 7. This is the second block, and 3, 3, and 3. This is the next. 1, 2, 3, and 4, 5, 6. This is the last one. Okay. So we will just look this. So first, in the first process, we will just take the 7 value, and we will write into this in increasing order. So 3, 4, 5, then 7, 9, and 10 and 13. Okay, like this. So this is the sorting order. Same thing we will repeat for the second block. So 1, 2, 1, 2, and next one is 6, 8, and
12, 15, 19.
12, 15, 19. Next block is
then 14.
Yeah, 14.
18, 18, 23. Sorry, 21, 21, 23, 24, 25.
24, 25.
Then
and next one is
11, 17, 17, 20.
20, 26, and 27. Okay, this one. So in this process, this is the process of this algorithm. You can see that in the code. First we are sorting, and we are returning this length flow division 2. So what is the length of the block is 7. Okay, 7 flow division 2 is 3. Okay, so that means 0, 1, 2, 3. So this value we are returning as a middle element. So we are getting this as a middle element for first block, this as a second block, this as a third block. And next is also 6 length, and 6 flow division 2 is also 3. Okay, so this is also a middle for next one. And we are getting this 4 value in the next block. So 7, 8. Then we will also arrange in the increasing order. So 20 and 21. So now this is the median of all the medians. Okay, so this is the list of medians. And then we will apply the same 4 flow division 2. So then we will get 2 index 0, 1, 2. This 20. Okay, so this will be selected as a median by this MOM algorithm.
So what if the fourth block had only 3 elements, let's say only 11, 17, 17?
So in that case, you will just use this 3 flow division to 1 index 1 element as a median.
So the next block that we would have made it 7, 8, 21 only, right?
No, that one also 17.
No,
because if you see this, what we are checking here, if len of L is less than equal to 7, we are sorting first and we are returning this as a median. Okay, doesn't matter how many elements it contains, it should be less than 7, less than or equal to 7. So if you have only this part, okay, if you don't have this part, okay, so you will return median from this block also. So by this 0, 1, so you will return this 17 as a median.
Okay.
Okay, so then this will become 7. After that 7, 8, and 17 and 20, and this will return as a median.
Okay, sir.
Okay.
Sir, after choosing this
Sir,
median for block, how we are choosing 20, sir?
No, first we are collecting the median of each block. Okay, so what is the median of first block is 7, second block is 8, third block is 21, and fourth block is 20. After that we will sort again this. This is a collection of medians. So after that we will sort again, then 7, 8, 20, and 21. Same things, what is the length of this? 4. 4 floor division 2 is 2. So 0 index 1, 2, 3. So 2 index is this one, 20.
Okay, got it, sir.
Okay, so this will be written as a median element by the MOM algorithm. So if block is given 5,
why we are sorting this 7, 8, 21, 20, where it is written in the code?
this one, no? L dot sort.
Okay, so for every lesser than or equal. Okay, got it.
Okay, no? If you see the lower part, we are just calling this, we are just taking this range, we are dividing the list, and after that we are sorting this part, and we are appending this value. Okay, so first condition is given. If we have lesser than or equal to 7, we will directly return the answer.
Above part is finding the mid element, and the lower part is making the blocks, right?
Yes, correct. So this part is actually making the blocks. If any time we are getting this length is which is less than or equal to 7, then we are returning the median directly. Okay, and this part, for this initial part, is actually creating the blocks. Okay. I think one small correction is required in this.
No, sir, it's correct. Like for after finding all the medians, we are calling mom of m. That's why we
It's recursive function, right, sir?
Yeah, this is recursive function. Yeah, this is recursive function we are applying here. So every time we are just applying the recursive. At any time we are reaching at the base case. So this is actually base case of this function. And we are reaching at the base case. Base case is when we are getting the block of the required size. Then we are returning the median value. Okay, so but you can remember the simple process of this. If we are giving the block of 5 elements, so just take 5 element and sort or each blocks, and then select the median. Then again repeat the process. If you are getting more than any number of elements, suppose if first time you are getting 10 blocks of where each contain the 5 element. Okay, so in that case you will get 10 medians. Okay, once again divide into 2 blocks of 5. Okay, repeat this process until you are getting till 1 element as the final. Okay, so this is the solution. Yeah, next one is this. Recurrence relation is given and complexity is asking in this problem. So this type of problem, you can remember the recursion tree process. So where the 3 condition is given. So if you look the slides of week 8 last. Okay, so you can remember this last property. Basically we can just relate our recurrence relation on this condition, this total cost. Okay, so you can just define the Tn, you can just relate your Tn, this recurrence relation, with this formula, and after that you can decide on each level a number of steps are decreasing or equal or increasing. If any of these condition is coming, so you will always get any one condition, either in each level or each calls the number of steps are either decreasing, either remains same, or it is increasing. If it is decreasing, then we will directly write the complexity using this Tn equal to big O Fn. If it is increasing, then we will just use this process fn into log n. Okay, and it is increasing, then we will use this formula. So I'm just taking the example of this. So for, if you remember the merge sort algorithm, okay, so what is the recurrence relation of merge sort? So Tn equal to, every time we call 2 times and with the size of 2, we divide the list into 2 halves, and we call 2 times the same merge function on the 2 part. And apart from that, we have one merge process. Okay, we just get the 2 sorted list and we merge them. And that process take, actually, if we have two sorted list of n by 2 and n by 2 size, then merge process will take n time. So the remaining complexity is n. So we can write as a order of n or either n, simple n. Okay, n steps is required. So this is the recurrence relation of merge sort algorithm. So how we can just figure out the complexity? So you can create a recursion tree for this. So what you can do, you can start from Tn. Okay. Now we will just create a recursion tree based on this calls. So this is the recursive call. This part is the recursive call, and this is the time required at each recursive call apart from this call. Okay. So that means from the first function Tn, we are calling 2 times. So Tn by 2 and Tn by 2. So 2n I am writing in that way, 2 child. Okay. And what are the time required for this is, so Tn by 2 and Tn by 2, total time is required n steps. N by 2 plus n by 2, total n steps is required. Okay. This is the recursive call. This will again generate 2 recursive call. So Tn by 4 and Tn by 4. Okay. Similar this one, Tn by 4, and this is Tn by 4. Okay. So if we have this n by 4 and n by 4 input, so merging process will generating by merging all these 2 lists. So n by 4 plus n by 4 plus n by 4 plus n by 4. Okay. So by merging this 2, we are getting n by 2. By merging these 2, we are getting n by 2, and total overall is n by 2 plus n by 2 is remain n. Okay. Similarly, if you repeat this process again, so you will get n by 8 in the next step, n by 8, and here n by 8, n by 8. Okay, this is the recursive call structure. So n by 8, n by 8. Similar this one, n by 8, n by 8. So this is the steps. This is the size of list at this level, and if you add all these steps, so you will get total 8 into n by 8, n. Okay. So now you can see that at each level, when we are calling recursively, but number of operation is remains same. At this first level call, we are getting total n steps for merging. At this level of the call, we are getting total number of operation n. Okay. So what you can do, you can just relate this recurrence relation by this r, this formula. Okay. So this one. So this is representing r, and this is representing, this 2 is representing c. Okay. And this part is representing fn. Okay. This additional part fn. And now you after drawing this recursion tree, you can see that the number of operations are not decreasing, not increasing. It is remains same at the each time. So the case is, we are getting this equal case. Okay. In this case, what you can do, you can just take fn, what is the value of fn, and just add this log n. Okay. So value of fn is n, and add this log n thing. So total will become log n complexity. Okay. Now the second example, if you look the binary search. Okay, one sec. Binary search, if you remember the recursion tree for binary search, so Tn equal to Tn by 2 and plus 1. So in this case, if you draw the recursion tree for this, so Tn, and we have only one call, Tn by 2. Okay, so number of operation is required at this level is 1, and so this is constant operation. It is not depend on the input size. We are comparing the middle element with the searching elements. Okay, so this is also 1. This is t n by 4. This is also 1. Okay, at that time we will reach at the last. So in this case, what is the value of fn? 1. Okay, 1. And you can see that at every stage we have equal amount of operation. So same case we are getting now again equal. So we will add fn into log n. So fn is 1 here and into log n, and we are getting log n complexity for binary search. Okay, so now similarly we can find out we can check this relation, it is increasing or it is decreasing. So based on that, so if you remember the fast select or quick select which is discussed in the week 8. Okay, so if I think that complexity is also given in this. Using the MOM, if we follow the MOM process, so what complexity is actually we got? It is junction median of median. Yeah. Yeah. Quick select become n log n using MOM. Okay, selection become on fast select algorithm. Okay, let's discuss this. The recursion. If we talk about the quick select using MOM, okay, what is the recurrence relation of the quick select? So recurrence relation of quick select is Tn equal to every time we just look the half size. Okay, so n by 2. But apart from that, the complexity is the time is required n operation. In that case, n operation is required. Because what is this n operation is required? This is for the partition process. If you remember the quick select process, we always first apply the partition process. We check the position of the pivot. Then based on the pivot position, we just remove one half and we check the remaining half only to finding the kth smallest element in our sequence. So in this case, this is the recurrence relation for our quick select using MOM. So what would be the complexity for this case? So in this case we have Tn, and every time you can see that if we have n, if we have n input, we are getting this n. Okay, now next time if we are getting this Tn by 2, now partition, if we are giving n by 2 size input, that means partition process will take n by 2 in the next steps. Okay, and next level we are passing t n by 4, partition will also take n by 4 time, because partition is just a process to just shifting all element before the pivot or after the pivot. So if we have n by 2 elements, definitely it will take n by 2 steps. So this is based on the input size. So here you can see that at each level this size is decreasing. Okay, at this level this is n, and this is n by 2, this is n by 4. So this is decreasing by some fixed constant. Okay, by fixed factor. So in this case, if our decrease, so this is the case of decreasing. So in that case, we can directly return the complexity Tn equal to big O Fn. So what is our Fn value is? This one, n. So for this, our complexity will be Fn. This is big O n. We can directly write the complexity big O n. If our steps are decreasing by some fixed factor at every time or decreasing at each level, so we can directly write complexity using this. Okay, so this is the decreasing case. Or if we just discuss about the problem which is given in the questions in mock, so what recurrence relation is given here? Okay, so if we look the first, if you look the first here, the recurrence relation is Tn and 9 t n by 3 plus n. Okay, so this is the fn value, and this is r value, this is c value. Okay, this. Now if you draw the recurrence relation for this, so what you will get, first step is tn. Okay, next step, total 9 call are there, that means 9 child are there, like this. Okay, so every steps we have tn by 3. If we have n input, we are getting n steps required at this level. Okay, so that means n steps are required if we have n input, and next input we have 9 times this call tn by 3 n by 3. So every times you have n by 3 steps required. Okay, so tn by 3. So this will also take additional this n by 3 steps. So in this way 9 times. So if you add all these steps 9 times, so 9 into n by 3, so you will get 3n at this steps. Okay, 3n. Previous was n, and this time this is 3n. And same time each child have 9 child. Okay, so this at this 9, same for this. This is 9, and size is n by 9 this time. Okay, for t n by 9 times. Okay, for each 9 child. So that means at this level 9 into 9, 81 times we will repeat this process n by 9 call. So 81 into n by 9. So 9, 9, this 9. Okay, so this will become 9n. So or what we can do, we can simply write this sequence like so: 3 to the power 0 into n. This is the first step. Next step is 3 to the power 1 into n, and next is 3 to the power 2 into n, like this. Okay, so we are getting this type of sequence, and this you can see that this is increasing. Steps are increasing at each level. So in this case, we use the last formula. The for last, this is the case of increasing case. At that time, we use this n to the power log cr, n to the power log base c and r. So we can conclude the complexity for this is, so what is the c value is here? 3. Okay, c value is 3, r value is recursive call 9. So just put this in the equation. So n to the power log. Okay, so log c value is 3, base 3, and r value is 9. So and you can also write this 9 as a 3 to the power 2. Okay, this 2 will come at the first before this log. So n 2 into log 3 3. So this will become 1, and this will become n square. Okay, and this will become complexity for this n square recurrence relation. So you can just look, just first draw the this recursion tree, and just look at each level when we are just expanding this tree. At each level, our number of operations are increasing, decreasing, or equal. So just you can directly use this formula. If equal, you can just put fn into log n. If it is decreasing, just use as a fn, and if it is increasing, just put this into the power log cr. So second problem, so this is for the first recurrence, and second recurrence is also given. So the answer for the first is n square. Okay, and answer for the second is same things we will check here. So t n equal to 4 t n by 4. Okay, plus n square. Okay, so here actually you can say we are giving n input, we are getting this n square at each level. So this is tn at the first time, and we are getting n square. In the next time, when we have 4 call, so this tn by 4, and this tn by 4, and same tn by 4, and tn by 4. So in this manner, if we have input n by 4, so what would be the total number of steps is required? N square by 16. Okay, same here, n square by 16, n square by 16, n square by 16. So total is 4 into n square by 16. So this is 4. So n square by 4 at this first level. So you can see that previous was n square and this time n square by 4. So this is decreasing. We are dividing by some factor. So this is a case of decreasing case. In the case of decreasing case, we just pick the Fn as a complexity. So just write the complexity is Fn equal to big O n square. Same n square. So answer will be this B.
Sir,
Yes.
today was the revision of week 7 and 8 also. So we have done only mock. So
yeah, so in mock also some questions is already discussed from week. So what are the important thing in week 7 and 8 is which I just discussed this recurrence relation. Okay, this part you should know. And in the week in the or in week 8, the remaining week 8 is 1 second. So this first thing is this inversion pair. This is also one important question. So generally asked in the many times. And this MOM we have discussed. Okay, so in BK, these are the important things. This inversion pair, some related information of this quick select and fast select. What is the complexity things? Okay, so if we are using MOM, then what are the required complexity? What is the complexity? If we are not using MOM, then what is the complexity of finding the largest element or the smallest element? So okay, so these three questions. Apart from that, in week 7, so this AVL part is important. AVL property you should know. Okay, and Hoffman codes are important, which I have just discussed. And greedy algorithms is interval scheduling, and this lateness problem. All things are actually I have discussed, which is important. And I have some other question. If you can stay, then we can also discuss. That is also some questions set from the previous quiz.
If you have time, can you explain question 1 also, sir?
One, I think we have already discussed in the initial.
Yes.
yes, sir, you have discussed.
Yeah.
You have discussed, sir? Okay.
Yeah, this we have already discussed.
Okay, I will watch on YouTube, sir.
So I have one set. Let quickly just check that if you know the answer. Okay. These are the also questions from the previous terms. If you already know, so I have approx 14-15 questions.
So this is already like 10:30. If for 15-20 minutes we can discuss some important topics which are not discussed yet, that would be better, I guess.
Yeah, so these questions are actually related from week 7 to 8. So I think that will be helpful. Okay, so I'm just quickly giving some hint. Okay, after that I will share this question set in the live session calendar link. You can also try later. So,
Okay, sir.
So I think it will take 30 minutes approx.
Okay. Sir, I have a small doubt. You can say if in week 5 and 6, like Dijkstra's, like there are some algorithm which we have read. So Prims and Kruskals both give us minimum cost spanning tree weight, right? Uh, but calculating the way we calculate, it's quite different. So I understood that one, but like Dijkstra's and Prims, how they are different, like process part, like I got confused in these algorithms in solution part only.
So the purpose of both algorithm are different. Okay, so in Dijkstra algorithm we are looking the shortest path from source.
Okay.
Okay, path
Single source.
from single source we are looking the path distance, shortest path distance for each node.
Yes,
Okay,
sir.
and Prim's algorithm is just finding out the minimum spanning tree where the tree should contain the minimum cost. If we add all the weight edge, that should contain the minimum cost, total cost. So this is Prim's is generating spanning tree, not the path anything. Okay.
Okay.
So purpose is totally different. The algorithm step is also different. So if I just let me just quickly check if any problems is not. Okay, so I'm just taking one example here for the Prim's algorithm and shortest path. Okay, so 1 second. This is A, B, C, E. 2, 5, 3, 1. First thing, Diast algorithm process. I'm just explaining. Okay, Diast algorithm process is to finding out the shortest path from single source. If we are taking this A as a source, then we will check what is the shortest path from A to all nodes B, D, C. And the process is like we just initialize with 0 and initialize with infinite with other. Okay, after that we just look from A. So this we just select one vertex with the minimum weights, minimum distance. So right now you can see that A contains the minimum distance 0. So we will select this first, and after selecting we will just mark this as a visited node, and we will just check the neighbors, direct connected nodes. What are the direct connected nodes from this A? So A to B, A to D, A to C. So that means we will just check that from A to B what is the distance. So A to D, A to B is 2, and what are the previous mark distance is infinite. So we always look the nodes which is not visited. If any node is already visited, we will not check again in the rest algorithm. So in this process, so A to B, we will check this 2 is the now distance from A to B, and this is the previous one is the infinite on B. We will update by 2. If we are getting a smaller one, we will update. Okay. Similar for A to C, previous on C is infinite, we will update by 5. A to D, this is we are getting A to D is 1, previous is 1. Now this is the first step. After that, same things we will repeat again. We will check the all unvisited vertex, and we will select the vertex which have the minimum distance. So in this case, we will just select this D, okay, because C contain 5, D contain 1, and B contain 2 distance from source. And then we will repeat this process again. So from D, we have two connected node which is not visited now, C and B, and we will mark this as a visited now. Okay, so visited, this is also visited. So D to B, 1 plus 1, previous is also 2, we are getting 2, same. Suppose if we have 3 here and this is 3. Okay, now we are getting this time what is the current distance of D is 1. So we are adding this 1 into the edge weights, because our final goal is to calculate the shortest path from source. So we will add the previous distance also. So what is the current distance on D is 1. So this 1 is representing A to D. And we will add this 1 plus 1. Okay, so D to B is 1 plus 1, 2. And 2 is smaller than the previous one. So we will update this 2. Same for this side. So here we are getting 1 plus 3 and 4. We are getting lesser than the previous one, 4. Yeah, we will update this. And we will repeat this process again. Now we will select the next node B. If we are selecting this B because B contains the smaller one, 2 and 4. And if you see that B is connected with the vertex which is already visited. So we will not doing anything. And same things for the C. C is already connected between A and D. Both are visited. So now all are visited. So final this process we are getting the shortest path distance. So A to B is 2. The path is A, D, and then DB. So this distance we are getting from this path. A to C we have 4. And path is A to D and D to C. And A to D is 1 direct. So this is the path information we are getting, shortest path value. And similar if we have suppose the same things for the spanning tree, C and D. And I'm connecting again, 5, 3, 1, 3. Okay. So suppose we were here, our goal is different. We want to find out the spanning tree. So that means all nodes should be connected with the minimum cost, total cost. So in this case, we will start from any node. Okay, so we can start from any node in this case. not any specific. Okay, so we can start from any node. Suppose we are starting from A. Sorry. So in this process, same things. We will just initialize with infinite all. Okay, 1 second. No, not infinite. Yeah, infinite. Sorry, 0. We are just marking these things. Uh, we will just set this A equal to 0 and infinite to all. But after that, what we will do, we will just look the all adjacent this time. So what is the adjacent of this A is AB, AD, and AC. So we have 3 adjacent. So AB, AC, and AD. This contain 3. This contain 5. AD contain 1. Okay. Now we will update this on this vertex. So like this is B is sorry, AB is 3, and this is 1, and this is C 5. But here actually in the next process we will just doing the same process. So we will also note down the previous weight edge weights. So in this case we will select the minimum vertex again. So we will select this D. We have completed this A. From this D portion, okay, then if we are selecting this D, that means we have selected this edge. Now in the next process, this time we will not add this one value into the B part. In the Dijkstra algorithm, when we visited this D, we added the distance from 1 plus 1, and then we are checking that we are getting smaller or not. This time we will only include this edge weights without adding the previous weights. Okay, because here this time we are interesting only in the weights edge with the minimum weights, which can be included in the spanning tree. So in this process, we have selected this one, AD equal to 1 in the first process. Now the previous is 3 and 5. From D we will check what edge is going on from D. Okay, so D to B, you can see that there is 1, and this one weight is smaller than the previous updated weight 3.
Yes,
Okay.
sir, got it.
Okay,
Got
now
it.
yeah, we will not add this value. This time we will just only use this 3. So this will be updated by 1. So that means
Sir,
this
we
will.
can. Sir, I got it. We can proceed with the question you have prepared.
Yes. Okay. So this is the difference.
Yes, sir, please.
Okay, one second. Not this one. Okay. So some questions based on the binary search tree.
Where you are sharing these questions, sir?
No, this currently I'm using. I will share this in the same calendar link. Okay.
Sir, you can share here as well.
No, this is not in the. This is currently not in the drive. This is in my local system.
Okay, sir, no problem.
Okay, I will upload the. I will upload this in the drive, and then we'll share the link after this session. So this is first question is given like this. This is a binary search tree, but characters are given in the this value are given in the form of character. Okay, but this is a binary search tree, and asking that what is the predecessor node in terms of value of the node M. Okay, so where is the M? This one. Okay, so what is the predecessor in terms of the value? So predecessor means the value which is coming closest to this value M, which is smaller than, but it is which is the closest one.
N.
Okay. No, not N. This you don't know what is the value actually we used.
Sir, I guess these are discussed by Sir Nath, sir.
We have discussed this.
Yes, in the TS session, I guess it is discussed these questions.
Yeah, so that maybe
No, sir,
maybe.
Please, sir. Sir, please you discuss, sir. You continue, sir. Please.
Okay. So actually, this is just a representation by the character, but it may be some value. But overall tree is binary search tree. Binary search tree means this rule should be follow. So every left child is should be less than the parent, and every right child should be greater than the parent, like this. Okay, this property is fulfilled. So this is a binary search tree, but we don't know the value, and we are asking that what is the predecessor of this m in terms of value. So predecessor means just nearest smaller value, and successor means just nearest greater value. Okay, so how you can just find out these things? So if you know the traversal, how you can traverse the binary tree or binary search tree? So you can apply the in order traversal for this tree. So in order traversal will generate a increasing sequence. In order traversal will always generate a increasing sequence, and after that you can simply decide which value will come just smaller than this m. And what is this in order traversal? So this is the recursive traversal things. So first visit the left side, okay, then print the node, then visit the right side. So this is the recursive call. Okay, so this is the recursive call, and this is a recursive call, and this is a simple print statement of the current node. So these are the three steps of the in order traversal. First, move to the left side and apply the same algorithm again on the left child. So we can simply write these three steps like this. So L, P, R. So just remember that print is coming in between. So this is the in order traversal, and this is left recursive call. Just move to the left child and apply the same three steps on the left child. Same things, this is the right recursive call. Move to the right child and apply the same three steps on the right child. So if we follow these things, if we use this print in between these two recursive call, left and right, so this is called as an in order traversal. If this print statement come first and this two recursive call come like this, print then left
one is left root and right.
Yeah, correct. L means we will just move to the left child, and we will apply the same three steps recursively on the left child. Okay.
In order traversal, what is the rules are? Left, right, and root, no?
No, left, node, and right. Okay, so this print statement I am just using for the print the current node. When we will just coming at this steps, we will print the current node. Otherwise, if we are at the L step, that means we will move to the left side, and then we will apply the same three steps on the left side. Okay, I will just explain one flow, and same for the recursive on the right. Okay, so this L and R the recursive call on the left child, on the right child. Okay, just remember these things. So this is in order. If we will just follow print first and then left recursive call, then right recursive call, then this is pre-order. And if we follow this L, R, and P, then this is a post order. So these are three traversal we used to traversing the binary tree or binary search tree. Okay, so to find out the answer for this, we have to use the in order traversal, because in order traversal will traverse the nodes in increasing order based on the value.
But print is nothing to do with the traversal, no?
Print is just a print statement. You can just consider. Okay, so I'm just explaining one thing. Okay, so here I'm using this LPR. Just remember, okay, I'm just showing you this second code. If you can see here this code.
Can you zoom, please?
Can you see this code?
Yes.
Okay, so this is just a traversal algorithm. So what type of this algorithm is actually? So we are currently at this T node. Okay, this is the current node. We are looking that T does not equal to none. What we are doing, we are just moving to traversal, same recursive algorithm. So name of the algorithm is traversal, and entering inside this, we are calling the recursive part on the T left. Then means we are calling the same algorithm on the left child, T left. So this is the L step, which I just mentioned. Okay, L step. Second step is traversal, same algorithm we are just applying on the right child. So this is R step. Okay, and this is the third one is the print statement. So what is the current node T and what is the value of T? Okay, print. This is the P step. So this LRP. So what type of traversal is this? So we are just using the print statement after L and R, then print. Okay.
Post order.
This is post order. Okay. So I'm just talking about these 3 steps, and I'm just writing in this short forms in the previous questions. So if you use this print statement in between these 2 recursive call, then it will become in order traversal. If you use this print statement before on these 2 recursive call, then it will become pre-order traversal. So these 3 type of traversal algorithm we generally used for traversing the tree. If we are applying this in order traversal on binary search tree, so according to the property of binary search tree, we will get the increasing sequence. So if this LPR, so that means first step will be execute first. Okay, so this L, this is a recursive call. That means we will move to the left and we will apply the same things. Okay, same things. L, first step will execute from here, and left call, then we will move here. Okay, LPR. Then we will, this is the again left recursive call, then we will move left child. Okay, LPR. But here there is no left child. So this step will not be executed. After that, we will execute the next step. This is a print statement. So this H will be print first. Okay. Then third step, write call. Write is also not there. So that means all 3 are complete. All 3 are complete. We will move back to the call. Okay. Now this part is complete. Then we will move to the second step of this. So this is P. This is will print the current node value. So this is D. Okay. And this is write recursive call. Write recursive call, that means move this side and apply the step LPR on the right side. Same, first step is this L, move to left, LPR. Okay, first step is left but no child. Okay, so then second step P, O. So this O will be printed, and then this R, this is no child R, so all complete. Now move back, left is complete. Now current P. Okay, so this I will be printed, and then move R. Okay, so move R, LPR. Left child is not there, then print statement P and R. Okay, complete this part. Now move back. This R part complete, so this part is complete. Now move back. So this R is complete. This is completed. Now move back here. So this is the recursive call I'm just explaining. So this L is first now completed. Total left part is completely. Now this is the print statement. So B will be printed here. Now this is the right recursive call. Move right. LPR. So this left recursive call. Move left. LPR. Okay. So this is the left. No left here. The P. So J will be printed. And then R. Okay. So all are completed. Now move back. This print statement E. And then R is there. Move here. LPR. And this left is not there. P is there. K. Okay. Now all part is completed. Move back here and back here, and now come here. Okay, so this L is completed. Now print statement A. Okay, then move to this side, LPR, then move this. Okay, so this first step L, LPR, left, LPR. So left, now print statement L. Okay, now this complete. This print statement F. R is not there, complete. Now print statement C. So R is there, so LPR, and then move here, LPR. Okay, and then we completed M and G. Okay, and then N. Okay, so in this manner you are getting this sequence of the nodes, and here you can find out this, what is the predecessor of this M. So this sequence is always you get in increasing order of the value for the binary search tree. So that means this C is the closest value which is smaller than the M. So C is the predecessor of M and G is the successor of M. Okay, so in that manner you can just find out the predecessor and successor value. So next problem, I've already explained which of the following order will be printed by the given code step. So here this is the post order is given. So
Sir,
that means,
sir, please show the previous screen, sir. 1 minute. Okay, sir.
okay. So second question is asking that, so this we can identify that which order we are following here. So this is the post order. That means L, R, P. So this thing. So same things we will apply on this L, R, P, and apply the same things. Okay. So left step is L, R, P. Left step L, R, P. Okay. So left is complete. Right is not there. Now P. So D will be printed. Okay. Same process you can apply on this step. So right is there. Yeah. So move here. So L, R, P. So left is there. L, R, P. Left is not there. R is not there. P. So H will be printed. Okay. Now this is completed. Now R is not there. Then P. E. Okay. Move back. Now print E. This one B. Same thing. Okay. Now come at this place. So this is the right part L, R, P, and left part L, R, P, left part L, R, P. Left is not there, R is not there, P. So I will be printed. R is not there, P. Okay, so F will be printed. R is there, yeah, L, R, P. So left is not there, R is not there, P. So G will be printed, and then C will be printed, and then this A will be printed. Okay, so this is the post order traversal. So in post order, you will always get the root node at the last. Okay. Root node will always come at the last position in the post order traversal. In pre-order traversal, you will get root node at the first place. Okay. So in this manner, you can just traverse the binary search tree. So traversal, you should know. Moving to the third one. So yeah, this is related to the previous questions. So which of the following statement is true about the complexity of the given function where n is the number of nodes? Yeah. So here actually we are asking that complexity. So or big O L log n, whether the tree is balanced or unbalanced. So what is the complexity of the previous operation? So it is depend on the tree's balance or not? I think no. So I'm just telling that because we are just traversing each node in this algorithm. Okay. So that means if we have n nodes, so we are traversing each node at least one time. So
And
in
sir,
this,
balanced thing come in the AVL tree, not in binary tree, right?
no, not this is not a case here. We are just asking that what is the complexity of this given code. But for this given code, if your tree is given in any manner, either balanced or not balanced, but still this algorithm will traverse each node, n node. Okay, so it will take order of n time. Doesn't matter what tree is balanced or not. So the algorithm is not actually depends on the tree structure. Okay, so it is just a recursive call structure and it is traversing each node. So the answer option C is correct. Big O of n, whether the tree is balanced or unbalanced. Yeah, if this type of question is asked for the like searching operation, if what is the searching operation will take the time if tree is balanced or unbalanced? What is the worst case time? So in this case, if our tree is balanced, then log n time is required for the searching. If tree is not balanced, so what is the worst case situation is if ever each node is connected like in this one child manner. Okay, like this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So this is also a binary search tree, but yeah. So but you have to just visit all the nodes if you want to search. This will become big O of n. So this type of question may be asked, like if tree is not balanced, what is the worst time complexity? If tree is balanced, what is the worst time complexity to searching? Okay. So for this question, so this traversal is always takes the order of n steps, either balanced or unbalanced. So here this consider binary search tree of height h. Which of the following statement is true? So in this case, some information is missing. Now this time we added this information. The base case is not given like what height we are taking actually. So if that statement is not, I'm just adding here. So we are just considering that if node tree have only one node, okay, single node, height is equal to 1. If tree have only single node, height equal to 1, h equal to 1. So just consider this case as a base case of this problem. then just discuss the answer. Okay. So this is the I think first term question. So because of that, this information is missed. So which option is the correct option? So the number of element in the tree is at most. So here this information is given. Height is given h. The number of elements in the tree is at most h. This is correct or not?
Yes, sir. Skewed
Wrong.
graph. Right now you just showed.
No, at most we are asking.
No, sir, wrong.
Okay, at most.
Hmm.
No, sir.
Maximum. So this is not the
So
case of
2h,
maximum.
2 to the power h minus 1.
Option D.
So this is incorrect. But this is the I think correct. The number of elements in the tree is at least h.
Yeah, least.
Yeah, least. Okay, so when each node are connected only this type. So this is the at least case, minimum case for any height h. So this is correct. The number of elements in the tree is at least 2h. So this is not correct because the B option is correct. The number of elements in the tree is at most 2 to the power h minus 1. Yeah, this is correct. Okay. If we are considering this as a base case, h equal to 1 for single node. So this is the correct one, 2 to the power h minus 1. This is the at most case. The number of elements in the tree is at most 2 to the power h. So this is also not correct. In the binary search tree, okay, so I think we have also discussed the similar question in the mock, which is based on this property. Okay, if number of nodes are given with the two childs, okay, so what are the number of leaf nodes? So there is one property you can remember, that the number of nodes with the zero child means leaf nodes. The number of leaf node will always be equal to number of nodes with two childs plus 1. This is one property of the binary tree. Okay, if you draw any binary tree like this, okay.
Now, how is it logically fits there? Always.
This is always true. So if you can just draw any binary tree or binary search tree. So if you just count the number of nodes with leaf node, I can explain. I can also prove this. So you can see here
N0 is the one which has no child.
Yeah, leaf node.
Leaf node.
Okay, so in this number of nodes with two child. And plus 1. So this relation will always be correct. Okay, so if you see the above tree, okay, so here you can see that number of nodes with two child is 2 and leaf nodes are 3. So 2 plus 1 equal to 3, same. Okay, so how we can prove this? So we can just relation the number of edge. I'm just explaining you once. So suppose we have one binary search tree. Okay, so if we have n nodes, if we are talking about for n nodes, okay, how many edge we required in the binary tree? How many edge are possible?
N minus 1.
Okay, so total number of edge is equal to n minus 1. Correct? And all the, if we count this like as a number of nodes with one child, so I'm just mentioning this n0 plus n1 plus n2. So these are the three possibility. So number of nodes with zero child, number of nodes with one child, number of nodes with two child. So only these three possibility are there. If we add this, so we will get n minus 1. Correct? Not n minus 1, n. Because we are counting
n includes the root node, no?
Yeah, all nodes are included.
Is it not n minus 1?
No. Here we are counting number of nodes with zero child, number of nodes with one child, number of nodes with two childs. That value should be
nodes,
equal to,
not the edges.
Yes, correct. Okay, so this is correct.
Correct.
So this equation is correct. Now, if you see the tree structure, you can see that node with two child will always be connected with two edge. Correct?
Yes.
Okay, so node with two child will always be correct with two edge lower than. Okay, node with one child will always be correct with one edge. node with 0 child will connect with 0 edge. So we can also write in this manner like, so number of node with n2. So 2 into n2 plus n1. This will become n minus 1.
Yes.
Okay. So, and we can just shift this 1 into the left side, so both equation will become equal. Okay. So like we can write like this.
This
2
equation
n.
is based on the edges, no, not the nodes.
This is based on the edge.
Right.
Okay. Here we are calculating the edge. So n2 is representing number of node with 2 childs, and we are just representing by multiplying by 2 number of edge. Okay. And same things for n1. n1 is representing number of node with 1 child, so that means connected with 1 edge. So we are just multiplying with 1, and this should be equal to total number of edge, which is n minus 1. Okay. And if we add 1, it will be equal to n. So I just shifted this 1 this side. So now both equation, if you see this, n above 1 is also equal to n, this is also equal to n. We can just put on the same side. So n0 plus n1 plus n2 equal to 2n2 plus n1 plus 1. Okay. So here what we can do, this n1 is cut, and after that this n1 will be reduced by this side. So this will become n0, and we will just shift this side. So this will 2n2 minus n2. This will become n2 plus 1. Okay.
Okay.
We are getting this. So this is the one property that will always exist in the binary tree. So this is also true.
So can you have the if option just in short, sir?
Sorry?
Sir, can you recap what just you did in short, sir?
Okay. So we are just trying to prove this equation. So this is saying that number of nodes with 0 child is always equal to number of node with 2 child plus 1. Okay. So we are just proving this by these things. So what we can do, we can consider that in any binary tree, each node maybe contain 0 child or 1 child or 2 child. So these 3 possibility are there. So we are just mentioning that n0, number of node with 0 child, number of node with 1 child, and number of node with 2 childs. So that should be equal to n. Okay, so n is representing total number of nodes in the tree. So this is the first equation we have just note down, and we also know that if number of nodes is n, number of edge will be n minus 1, one less. So now we can write that, we can write like this. So number of nodes with 2 child will always be connected with 2 edge below. Okay, so if you see this node, so this contain 2 child, so that means 2 edge are connected below this direct. Okay, so this is the one things. Now we are counting the number of edge by the different way. So n2 into 2. So this will be representing the number of edge which are connected to the number of node with 2 child. So total edge we will count. Then the another edge will is coming from the node with connected with the 1 child. Okay, so like this, the second node, this is connected with 1 child below them. Okay,
we are multiplying by 2.
So no, we are multiplying by 2 and 2 into 2, but we will not multiplying by 2 with the n1. So this is only n1, because every node is containing only one edge which has the 1 child. So this is representing simple 1. So
and
this
like we are multiplying just because it has 2 child.
So if you just look this same tree, okay, so if you look this tree, so how many nodes have 2 child? So okay, this is the 1 and this is the 1. So we can calculate the number of edge like the 2 into 2. Okay, so 4. And how many nodes which have the 1 child? Only this 1. Okay, so plus 1. And other are the leaf nodes. So there is no edge connected below them, the leaf nodes. So total you can see that we are getting 5 edge. So total you can see in the tree. So 1, 2, 3, 4, 5 edges there. So same formula we are using, number of nodes with 2 child into 2 and plus n1, because we can write like this, n1 into 1. So this is representing total number of edge, which is equal to n minus 1. Now we are simply solving these two equation by equivalence formula, and then we are getting this n0 equal to n2 plus 1. This is true. Now you can check these things by looking any binary search tree or binary tree if this is following or not. Okay. So this is one property. Just remember this, n0 equal to n2 plus 1. So this type of information is given, maybe given some questions. So some n2 value is given. What would be the leaf node? So suppose if the question is given like this, so number of node with 2 child is 10. So how many leaf nodes are there? So you can directly use this formula. So just add 1 and return 11. Okay, 11 leaf node will be there. Okay, so yeah. So next question is this, one chronological order of is given for the activities or meeting. We can say that. So this AS is representing start time, or this BS S is representing start time, or E is representing end time for the activity. And chronological order means we can just give like time, like okay, 1 2 3 4 5 6 7 8 9 10, like this. Okay, 12 13 14 15 16. So this is the chronological order. So if AS is starting at 1, now A is ending at time 4. So how many minimum number of rooms is required to perform all these activity? Okay, so what we can do, we can simply just note down these things. So AS is starting. Okay, so AS is starting in one room. Okay, so this is one room is required for AS. This is running, and then next time BS is starting. Okay, so we have to definitely use, because AS is not completed, we have to use second room for BS. Okay, CS is now not completed, CS is starting, but A and B is still running, so we have to use third room for CS. Okay, now AE is completed at time 4, so we can cross this, that this is completed, that means room 1 is available now. So DS is now started, so we will just use this DS here, one room. We will not use the new room, because AS is now completed. C is now completed, so we will finish this. Now this is available, we will use this for the next. So ES is started, so ES, okay, we will use this. And BE is completed. Now FS is started, so you can see that we are using the same 3 room now. Okay, no need to use extra room. Now DE is completed, GS is started, we will use the same. And EE, so this is completed. HS, so HS we will use this one. And FE, this is completed. GE, yeah, this is completed. HE, this is completed. So during this process we need only 3 room. 3 will be the answer for this. So you can solve in this manner. Yeah, this is Huffman tree. So I hope this is okay. Do I need to explain this? So frequency, this probability is given, just create a Huffman tree based on this, and you can solve. So I'm skipping this. Okay, so this is binary search insertion operation. So you can simply create the binary search tree quickly. So 50 first node, add one node one by after. Okay, so one by one. So 80 add in this. So 80 will be added on this side. Now 20 is smaller than 50, so 20 will add here. 60 is greater than 50, smaller than 80. Okay, so 60 will add here. 10 is smaller than 50, then 20, then 10 will add here. 45 is smaller than 50, greater than 20, so 45 will add here. 65 greater than 50, but smaller than 80, then greater than 60, 65 will add here. 30 smaller than 50, greater than 20, smaller than 45, 30 will add here. 90 greater than 50 and greater than 80. Okay, 90. So during the insertion of binary search tree, always start comparison from the root node every time, and just move accordingly, and once you find out the empty place, add. Okay, so what is the maximum depth of this? So depth of, you can see that what is asking that the elements at the max depth are, so max depth elements are 30 and 65, so which are coming at the lowest. So these are some property of the AVL tree. We can find out the minimum number of nodes in the AVL tree if height is given. So in this sequence, you just remember that this formula SH equal to SH minus 1 plus SH minus 2. Okay, so this is wrong. Okay, so this is not the correct answer. So here we use the formula SH equal to SH minus 1 plus SH minus 2 plus 1. Okay, and we always start from the first thing. So we know that S0 equal to 0, S1 equal to 1. Yeah, please turn off the mic. Akash. Okay, so correct formula of this to find out the minimum number of nodes in the AVL tree is SH equal to SH minus 1 plus SH minus 2 plus 1. Okay, so this is not correct, which is given in the option. So S0 equal to 0, S1 equal to 1. So sometimes this type of question is asked like height equal to 4, then what would be the minimum number of nodes in the AVL tree? So you have to use this formula from the start. So S0 equal to 0, S1 equal to 1, you know. But S2, you have to calculate like S0 plus 0 plus S1, then plus 1. Okay, so you know 0 plus 1 plus 1. Okay, so 2 value. Now S2 you know, now you can calculate S3. So then S2 plus S1 plus 1. Okay, so this value is 2, this is 1, and this is 1. Okay, so total 4. Now S4, you will get S3 plus S2, then plus 1. So S3 is 4 plus S2 is 2 plus 1. So this is 7. So 7 is the answer like this. Okay, so for height h equal to 4, 7 is the minimum number of nodes. And for the maximum, so formula will remain same, 2 to the power h minus 1. This is for the full binary tree. Maximum number of nodes. Okay, so because this ABL tree is balanced tree, so searching operation will be performed in log n time. So this is also true. Okay, and the complexity of both insertion and deletion is, so this is not true because insertion and deletion operation will also be performed in log n time because our tree is balanced. And this is balance factor things. In AVL tree, the absolute difference between the height of the left subtree and the right subtree of any node can't be more than 1. Yeah, this is correct. Okay, so just remember the AVL tree property which we have followed in the questions. So I hope this is, you can do some sequences given, create the AVL tree for this. We have discussed already these things, prefix code. This when codes are given, you have to figure out that which code is not possible. So just look the prefix things. In each code, just check any code is coming as a prefix code or not directly. Okay, so 1 is not coming as a prefix, but 10 is also not coming. 01, you can see that 01 is coming as a prefix in this part. So this is not correct. Okay, similar for this one. 10, yeah, here you can see that any code is not coming as a prefix code in the B option. Okay, so just look this property, prefix property, any code is coming as a prefix or not. So here you can see that this 101 is coming as a prefix of this code. This is not possible. Okay, so similar 10 and this 00, and this is also not okay. So yeah, this is MSQ. Okay, so this B and D is correct for this. So this is interval scheduling. We have discussed already. Just sort the activity based on the end time and solve. Okay, so this interval scheduling we have already discussed many times. This inversion pair we have discussed. So MOM based, this is also use the following statement is true. Using MOM, the worst case running time for find kth largest will be order of n. Yeah, this is correct. Using m, the worst case running time is n log n. So this is not correct. Finding k at largest. Yeah, this is not correct. Using m, worst case running time, quick sort will be n log n. Yeah, this is also correct. Okay, so just remember this property. When we are using MOM, so that means we are finding the pivot and that will come in the middle. So that will become a best case. Yeah, this is also inversion pair related. We have discussed this complexity questions also, so I think you can try. If anyone have any doubt in this recurrence relations, so we have already discussed this one for the quick select. Okay. No, this is not the quick select. This is for binary search. We have already discussed. Okay, this is simple. N minus 1. Okay, this type of thing. So t n minus 1 every time. So this is a sequence of like n minus 1, then n minus 2, n minus 3. So this will become n square. So this will generate n square complexity. This one. Okay. This is binary search related. So this will generate log n. And here this is the similar type of merge sort. Okay, so 4 call with each time. So that means we will generate 4 child where the n by 4, n by 4, n by 4, and n by 4. And here it is n. If we add all these, so we will get n. So same at the each level. So in that case, we will just consider that fn into log n. So this will become n log n. So this is equal to this one. Okay, in the above case, this is 2 child, so tn, and every time we have n by 8, n by 8. Okay, t n by 8, t n by 8. So here this is n. Now this, if you add this n by 8 plus n by 8, 2 into n by 8, and this will become 4. So n by 4. So you can see that here this is n. Next step n by 4. So this is decreasing. So in the decreasing case, we always pick the fn as a complexity. So this will become fn.
So the B part is increasing or decreasing?
Equal case.
So in the equal, we need to take the
fn
log n.
Fn into log n.
Fn log n.
Okay, so fn is n here and log n. So n log n total. Okay, so some extra is there. So this is I have discussed for the quick select. So extra time is required for partition, and this is n by 2 part. Okay, so in this case, every steps you will get this like tn. We have n. Next step t n by 2. We will add n by 2. So this is decreasing. Okay, so decreasing case, select this as a complexity. So we become order of n. So here this is similar to this is exact merge case. So this
is it same for quick sort also? Quick sort also same thing. Previous
yeah, this one. No, this one is the quick sort best case.
Okay.
This one was the quick select.
Quick select. Okay.
And quick sort worst case is actually tn equal to tn minus 1 plus quick of n. So this is the quick select worst case, and this is coming inside this one. Okay, if our pivot element is coming on the any one side, either left or right, so we will just apply the same quicksort algorithm on n minus 1 elements, and partition will take n time. So this is the worst case. And last question is this one. This is increasing case. So so tn we have, and 4 call we have. Okay, so n by 2, n by 2, n by 2, and n by 2. Okay, 4 call. So here this is n. Next step it will become 2n. So 4 into 2 n by 2 is 2n. So this is increasing case. In the increasing case, we use the formula n log cr. Okay, and cr is 4 and c is 2. So n log base 2 and 4. So this 2 to the power 2. So this will become n square. Okay, log 2 and 2. This will become 1. So n square. So complexity for this is n square. Okay, so this was the last one. Okay.
Sir, can you share this the PDF in the Google Drive right now, sir, and the link here in chat, sir, so we can see it once again.
Okay.
So you told one direct formula for finding the leaf node. Can you repeat that?
Finding the leaf node. Yeah, that if okay, 1 second. Yeah, if suppose this type of information is given, so number of nodes is given with 2 childs. So if n2 is given like 10, what is the value of n0? So you can directly use that formula, n0 equal to n2 plus 1. Okay, so here answer will be 11. Similar things, if number of leaf nodes are given, like 20, number of leaf nodes are given 20, and asking that what are the number of nodes with 2 childs, just use this n0 minus 1, 19. Okay, so this direct formula, if it is given in this manner. And some question is also related to the pre-order, post-order, and this traversal is given. So how you can generate the tree? So if pre-order is given, so definitely root will come at the first place.
First, yes, sir.
So you can just make the root node. Suppose this is the information like 20, 30, 5, 4, 3, 8. So like this is a pre-order of any tree. Okay, so you can generate a binary tree, search tree for this. Okay, but not for the binary tree. I'm talking about if pre-order is given for binary search tree, then you can create a tree. But if pre-order is given for binary, only binary tree, then you cannot create a tree only using the one order. Then you need 2 order required. So that in order, or maybe in order pre-order, maybe in order post-order, or pre-order and post-order. 2 combination is required to generate a binary tree. But for binary search tree, you can simply add like this 20 first. You know this pre-order first node is the root node. Create the first node as a root node, and similarly add all the elements in this sequence left to right. If sequence is given post order, suppose same like 20, 30, 5, 4, 3, 8. If this order is post order,
Sir, then root will be 8.
Yeah, root will be 8, and you have to insert the element from right to left.
Yes.
Okay, so 8, then you have to add 3. 3 is smaller than 8, so 3 will add here.
Sir, how can we predict the binary tree from these 2 traversals?
Yeah, for binary tree, you have need actually pair, either in order with pre-order, or in order with post-order, or pre-order with post-order. So this combination is required to generate the tree for binary tree. Because in binary tree there is no relation between child, left child, or right child, or parent. So we cannot generate the same tree by looking only one traversal. Okay, so that things. Do you want to discuss? I think if you can stay, then I can explain. But we have to calculate the first binary tree again. Okay, let me just quickly discuss. So suppose I have one binary tree like 10, 20, 30, 40, 5, 6. Okay, this is simple binary tree I'm looking here. So first I'm just calculating the in-order traversal for this. In-order traversal. So in-order traversal, we have to calculate this. So 10, 20. So I'm just directly writing, okay. So 40, then 20, then 5, then 10, then 6, then 30. Okay. So this is the in-order traversal. Pre-order, if we look this, so print LR, okay. So 10, and then we move to the left, 20, move to the 40, and then 5, then come here 30, and then 6. Post order is LRP. Okay, so post order will be then move to here. Okay, 40, then 5, then 20, then 6, then 30, then 10. Okay, so I have just created this 3 order for the given tree. But if suppose this order is given, so how we can generate the same tree by the given order? So we cannot generate the tree by using this one order. Suppose this in order is given, only this one order. So we in order we cannot decide what is the root node. This is the same for the binary search also. Okay, so if in order is given, you cannot create binary search tree because you don't know which is the root node. But pre-order, you know, this is the first is the root node. Post order, you know, last node is the root node. But in the case of binary tree, we need two order at the same time. So suppose in order and pre-order is given. So okay, so 40 I'm writing in order, then 40, 20, 5, 10, 6, 30. Okay, and pre-order is given like 10, 20, 40, 5, 30, and 6. So by these two combination we can create the binary search tree. How we can create? Because we will just look this pre-order, because we know that the first node is the root node. So we
The
will
root.
create this 10 here. Okay, after that we will just look the position of this 10 in our in order process.
In order.
Okay, all nodes which are coming on the left will
Will
always
be left side.
left side. So I'm just writing the sequence here. So 20 and 5. Which are coming on the right, I am writing the sequence on the right. So 6 and 30, same order. Okay, now we will just traverse this pre-order from left to right, and we will mark as a node. Okay, at the current time. Okay, so this 20 is the next one. So 20 is here now. Okay, this is in this sequence. So 20 will be added as this label. Now node which is coming on the left side from this 20 will be come on this side, and those are coming on the right side will add here. Okay, now next node is 40. So 40 we will mark as a node. No node is on left or right, so no problem. So 5, yeah, we'll mark as a node. And 30, yeah, 30 we will select here. So 6 is coming before this, so that means this will connect on this side. And next node is 6. So you can see that. Okay, so we are getting the same binary search tree. So same things for the post order. If in order and post order is given, so 40, 20, and 5, 10, 6, and 30. Okay, and post order is given. So this is in order, post order. 40, 5, 20, 6, 30, and 10. So in post order case, just look traverse this from the right to left. So this 10 is a root node, so mark 10. And just check the same things on the in order. Okay, so all these are coming on the left. So 40, 20, and 5, and this is 6 and 30. Now next is 30 from this side. Okay, so 30 will be marked at a node. So 6 is coming on this side, 6. Then 6, this will mark as a node. And next is 20. So 20 will be selected. So 40 will come this side, and 5 will come this side. Now 5 will be marked as node, and the 40 will mark as node. Okay, so you will get the same. And that pre-order and post order is given, then this is little bit logical. Okay, so I think that is not required. Little tricky. I can try like this also. Pre. So 10, 20, 40, 5, 30, and 6. Post 40, 5, 20, 6, 30, and 10. These two order are given. So in this case, there is a chance to develop the different tree, but you will get the same order: pre-order, in order, post order, but the structure may be changed if pre-order and post order is given. This is because if we follow the rules, so if you know that this 10 and 10, this is representing the root node 10. After that, in the pre-order, okay, let me just quickly remember the logic for this. Okay. Pre-order right on 20. Okay, so this pre-order, so we actually every time we calculate the two things for the each node. If we are calculating the what are the left child or right child for this 10, so we will just check the what is the next node on the right side of the pre-order. So that will mark as a C1 as a left child. Okay, so I am just writing down L. Okay, so that will be considered as a left. And what is the just previous node in the post order, that will consider as a R
Right.
of 10.
Right.
Okay, so here L is 20 and R is 30. Okay, so this node is selected like this. So R, this is L. So we will add in this manner. So we are getting two different. So we will add this 20 on the left and 30 on the right. So same things. Now we will check for 20. So 20, if you see the 20, you have this left value 40. Okay, 40. And here, what is the value of the previous of this, like this? Okay, so this is representing right of the 20. So this is the L of the 20 and this is the R of 20. So based on that, we will just add this. So left is 40 and right is 5. Now this node is marked. Now we will check for 30. So 30 is here. So what is the yeah, in this case, yeah, this is the one problem with this. So you can see that 30, what is the right side of this 36? So this is representing left child. And same here, what is the node before this 30? This is also 6. So this is representing R. If this L and R is representing the same value, so that means these are pointing to the same node. So in this case, if L and R both are same, so we can connect either on left side, either on right side. Both are correct. So this may be create a different structure here now. So based on this information, we are getting L equal to 6 and R equal to 6. If value are not same, we can create easily left child and right child. But if value are same, then we can connect either on left or right side. So we cannot identify that which node is actually which side is actually it is connected in the actual tree. So if we connect this side, then still you will get the same in order, pre-order and post order for this tree. Okay, so it may be connected on this left or right in this situation. So this is marked now. Now if we will repeat this process, so we will check for 20, so not 40. So 40, if we check for 40, so you can see that this is right is coming on 5, but 5 is already marked as a node in our tree. So we will not look this. It's already marked. Okay. And if we look for 5, so 5 right is 30, 30 is also marked. So we will not check this. Similar for this, 40 is also marked. Okay. So but we are getting the similar, we are getting the binary search tree, but the substructure may be changed if any node contain one child for this situation. Okay, so for binary case, this is the required information to generate the binary tree. Okay, I hope many things are covered. Any query?
Sir, question number 6 in previous year question, sir.
I don't have the previous question. Can you just share the question?
No, sir. Sir, which you have discussed before this.
Okay.
Yes, sir.
In
Question
this,
number 6, sir. I have no idea about that.
This Huffman tree?
Yes, sir.
So this probability is given. Okay. So in Huffman tree, just always pick the two smaller frequency or probability first. So what are the smallest frequencies there? 11,
0.11 and 16.
16. Okay. So we can just create a leaf node for these two. So 0.11, I am just adding this, or I am just taking the decimal part value. Okay, so 11, like this, 11 and 16. So 11 is representing E and 16 is representing C. So we will create a Huffman tree for this, and I am getting 11 plus 16, 27. Now we have already marked this one and this one. Now the new weights are this 22, 21, 30 and 27. So select the next two smaller out of this A, B, D and this internal one.
D. Okay, sir.
Okay, so this A and B are the two smaller, next two smaller. Okay, and this is the actual frequency of the character. So we will just create a separate leaf node for this. So you can write like 21 and 22. So 21 is representing character B, and this is representing 22 is representing A. Now add this, you are getting 43. Okay. Now we have used this one and this one also. Now we have three weights remaining. So 27, 43 and 30. So which are the two next smaller is 27 and 30. Correct? So this 27 is internal node, this 30 is the actual. So actual one will become as a leaf node with this 27. So 30. Okay, and you will get 57. So now we have only two remaining, 57 and 43. This will be added 100. Okay, now this is the Huffman tree, and now we will mark left edge is 0 and right edge as a 1. So 0 1 0 1 0 1 and 0 1. Now calculate the codes for each character. So A, what is the code for A? So just traverse from root to A, leaf node. So 1 and 1, what edge value is coming in this path? 1 1. B, for B the edge value is coming 1 0. C value is coming 0 0 1. D code is coming D, where is D? This 30. Okay, so this is D. So 0 and 1. E is coming 0 0 0. Okay, so this is now Huffman codes. And what is asking, how many bits will be used to encode the message A, B, C, D, E? So how many bits is required for A is 2, B is 2, C is 3, and D is 2, and E is 3. So add this value 2 plus 2 plus 3. So this is 7 plus 2 9 plus 3 12. So total 12 bits is required to generate the code for ABCDE message. Okay.
Okay, sir.
Thank you, sir. Thank you so much.
Okay.
Thank you, sir. Thank you.
Okay, so I hope all the things is clear.
Thank
Any
you,
other?
sir. Good night.
Okay, thanks everyone. All the best.
Thanks, sir. So the PDF will be uploaded, no?
On the calendar event, I will upload the link.
Okay. Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.